Well, hello there, everybody. Welcome to SkyTour live stream for this wonderful November 19th, 2022. It's nice to see a lot of people joined us already. It's very nice. We will be looking at a few objects tonight, mostly stuff that I feel like looking at. I actually decided to do a stream probably about 3 minutes ago, so I apologize for the short notice. And if Daryl wants to come in, he can. I don't know where he is. I haven't even tried to talk to him yet. You know what happens? You open the observatory, you start peeking at stuff, and you look around. Next thing you know, you're hitting go on the stream, thinking, wow, I just started streaming. Oh boy. So I didn't even think about it. So I'll ask him if he wants to join. If he doesn't, that's fine. You know, I can't expect everybody to just hop to just because I start doing something. So I'll find out. In any case, I see some folks here that I have not seen here before. All right. I'll say hi to Jim Merrill, who's here, and Proficient Epic 300. How you doing? He says, I joined at 6 a.m. when everyone was sleeping. I know, including me. I let it run all night unattended just to see what would happen. And, well, I haven't reviewed it to see the meteors that we may or may not have caught. So it turned out to be, well, I don't know. I was okay with it because I set up our high-res camera out front and just let it run. Very cool. Yeah, So Daryl says, sure, already going? Yes, already going. The star in front of us here, this is Diphda. Okay, Diphda, all right, I can show you that star actually, just so you get an idea. We'll bring up our planetarium view, and here's Diphda. And if we zoom out, you can see where Diphda is in the sky, all right? And you'll notice that Diphda is just kind of down below Jupiter. We're in the constellation of Cetus. Okay, Cetus, of course, is the sea monster. So that's what you see here is the sea monster of Cetus. And there's some other cool things that are in Cetus. We don't have a moon tonight to worry about for hours and hours. I'm not sure if I can handle hours and hours, but we'll see. We will see. So I think Daryl wants to join, so I will tell him, he can join if he likes, and I will bring him in. Let's see. All right, let's find out here. All right. As I said, I just decided to do this last minute. It's kind of like, whoa, you're streaming. I didn't even know I was streaming until I hit go stream. But you know what? That's what's nice about this. When you know your astronomy, you can just go anywhere in the sky and find something cool to talk about, right? And that's kind of what I do. So I'm up for it. Interestingly, okay, I'm hearing. Okay, we're talking about an object caught in the other stream the other night. I'm just going to send Daryl a message now. So Diphda's in Cetus, the sea monster, and it's kind of a neat constellation. It kind of wanders through the sky. Daryl seems to be ready, so let's give him a call. Sorry about the Skype sound. Actually, you won't hear the Skype sound. Hello, Daryl. How are you doing?
I'm okay, you?
I'm alright. So, I didn't know I was going to stream until, well, I don't know, about 6 minutes ago. And I just found myself hitting go on the stream. And I was like, I got to do it. Why not, right?
Okay.
Yeah. I want to thank everybody who joined us on the Meteor stream. The Leonids this year turned out to be kind of a dud. But there were some cool things caught on some other streams, and we did catch a couple of really neat meteors. And we'll talk about that, as time moves on. I want to say hello to the early arrivals here. Okay, first one was Renee Cruz. Hi, Renee. How are things down in South America? And Hay is with us. BG, naturally, that's Petita in Pennsylvania. CND Boy is with us. And Paul Atreides is with us as well. And Daisy and Zoe Amethyst, how are you guys doing? You know what I haven't seen lately is I haven't seen Lane. What's going on? Where is she? We want to see Lane. You know? And let's see, I think that one of the things that we also want to do is I want to say hello to Mary Kaczynski. Hi there, Mary. Good to see you. And Proficient is with us. Nice to see you as well. And we also have Paul Atreides, I mentioned, and Claudio Ramos from Chile. Hi, Claudio. How you doing? It's nice to see you again. You're going to see a little bit different activity. I mean, we normally do what you're about to see tonight, the deep sky with really cool objects in the night sky. And Zadarak is with us. Good to see you as well. Let's go. Really cool. Cyclone, what's happening? Cyclone says, I was so tired last minute. I never saw the Leonid meteor shower. Well, that's okay, because the Leonids weren't really all that impressive this year. Robin Curtis is here. Michael Galea, W is with us. Good to see you. Alanis, hello. Nice to see you. So if you guys have any requests, if you know of objects that are in the night sky overhead now, you can certainly ask for them. Otherwise, we will go on our little autopilot adventures. So we're in Cetus right now, Daryl, as you can see. And I'm wondering, since we're here, we're not that far from Aquarius and the Helix Nebula.
Yep.
So I was thinking maybe we should check that out since it's going to be gone soon.
Yeah. Time flies.
Gone for the season, that is, not gone forever. All right.
Of course.
Yeah. And so if we actually were to look that up, it would actually show up on the list here. You'll see it. It's down here. We'd have to zoom in a little more to see the symbol. But we're going to go there. We're going to check out the Aquarius Helix Nebula. And there we go. So we're going to tell the telescope to go there now. So you watch the telescope's going to move up there. There it goes. And it's going to move right to the Helix Nebula. You should see it show up in our night vision mode. You should see it show up in here. There it is. There we go. There's the Helix. Dude W says, gotta love to pick on Mark just because just to mess with him. Hey, you know what? I have a thick skin and I know it's all in jest, so I never take anything to heart, so don't worry about it. You know, you can't have a thick skin when you're doing this stuff. And don't forget, you know, what I do most of the time is I tell people that UFO they captured on their phone is probably not a UFO. You know, and that's unfortunate. People like to know they caught something really incredible, but it's unfortunately not always the case. Sorry.
Did you see the message I sent you earlier?
About what Bill caught on the stream?
Yeah.
Yeah, Bill sent me a message too. I haven't looked at it yet, but I will.
It's very interesting.
All right.
Odd looking.
Okay. I will check that out. Hey, you know, when you're looking at a Leonid stream, you don't always catch meteors, right?
Saw a few last night.
Yeah, we did on our stream,
Yeah.
and I'm sure other people caught them.
There's Izabela. Hello, Izabela.
Hey, Izabela. Good to see you, Izabela. Thank you very much for coming out with us tonight. So, folks, tonight you get to see a SkyTour live stream doing what we normally do. And that is to look at deep sky objects. This object here we're looking at is called a planetary nebula. And this is not the best it's going to get. We're going to actually have it looking so good you're going to wonder how in the world we do it. But first, before we do that, we're going to connect our focusing system. All right, and there it is. And then we're going to move the focus out a little bit and then do a critical focusing procedure to get our telescope finely focused. And you'll watch the stars become little donuts here in just a second. There we go. And we'll go one more, and it'll be very much out of focus. Okay, there we go. All right, and then we're going to come into our focusing tool, and we're going to do what's called a full width half maximum focus, and we're going to scan in the direction that brings it into focus. And the idea is to build a curve. You'll see a curve over here. It'll be like a parabolic curve. The bottom of the curve is the point of best focus, and there'll be a line there. And when we tell it to focus on that, it's going to move the focuser right to that spot and make these images look absolutely sharp. I have never been disappointed with this focusing program. It actually performs quite well.
When you focus with an extended object in the field of view, like the Helix there, that doesn't play hob with the focus. It looks like it's ignoring it. Well, no,
it does. Yeah, but see what it's doing is it's picking only the stars, the points. It might pick a star in a nebula. It might pick the central star in a nebula too. But for the most part, it ignores it.
Okay.
All right.
I've wondered. Sometimes I see you know, if we're on an object, you'll move over to the side to get it out of the field of view when you focus.
I have done that, and tonight I'm not, and just to see how it goes. I mean, you can see how the focus is really gradual right here, but it's starting to climb back up. So I think the central point of focus is about here, and there we go. It's just as I said that. The focus point shows up, and when this line turns green, we should see it give us a green line right about now. There we go. And so now we say go to that point of best focus. So the focuser is going to shift all the way to the other end and all the way back again. There it goes, other end, and all the way back to the center to this interpreted focus spot, right? So now this image is absolutely sharply focused, okay? And the temperature out in the building right now is 14 Celsius. So we're in the 40s, I believe. 40s or 50s, maybe. I don't convert Celsius in my head.
10 degrees Celsius is 50 degrees Fahrenheit.
Okay, so we're in the 50s now, yeah. And so now I set temperature compensation. I came up with an equation that'll actually move the focus as the temperature changes, which is really cool because as the temperature changes, focus points change. All right, so that said, let's do this. We're going to zoom in on this object a little bit. Doesn't look like much, does it? But here's what we're going to do. First of all, we have our guide star. You can see the guider is guiding now, okay? And as these numbers change, it shows that it's moving a little bit left, right, up, and down in order to maintain a guider position. If there's any wind, that will throw it off. So I don't know how windy it is out there. We're going to find out. But first thing I'm going to do is try and do a 30-second shot. This is a 30-second exposure on this system. Off it runs, and down here in the lower right corner, all right, just to the left of the SkyTour LiveStream logo, you can actually see a progress bar. When that progress bar gets all the way over to the right, we will be ready to show them. You like to remove that logo, and then it'll do the exposure and put it on the screen. So we have 8 seconds left, and we'll see what it looks like. And now this will be like one of the first ones you'll actually see what it looks like. So this is the night vision view, and this is the non-night vision view, okay? And what we're going to do is we're going to stack them. And right now, this image stack is one that will start with the next data. I should just clear this, and then it'll bring in the next one. All right, so we're reset. Here comes the next one. There we go. What a difference, huh? You can see a lot more in here. Now, all this modeled look, this is noise. And what we're doing is we're taking an image, taking a second image, aligning it with the first and stacking it. And doing that over and over and over to create an image sandwich. All the data, even the faintest dark or bright nebulous detail, is going to rise to the top. And the noise, which is random, is going to get averaged out. So watch how much the noise changes right now. Ready? Boom. See that? A lot of the noise went away. And it's going to continue to get better and better and better. Right? And we can color correct this right now. And now you can see it even looks greater and even better. And we can alter the curves a little bit to just make it look a little better. This is our data right here. You see that? This is our data. And this yellow curve is the curve that intercepts the data. So if we were to slide this over some more, we'd notice that it gets brighter and brighter and brighter because more data under that curve is being brought in. All right. So that's kind of how it works in general, right? But this is a beautiful planetary nebula. It's the biggest one in the sky and the closest one to us. And it's called the Helix Nebula. And the Helix Nebula, all right, it has a distance of just, people say between 500 and 600 light years. But planetary nebula like this, the remnants of dead stars, all right, they form when the outer envelope of the star just drifts away from the star once it becomes a red giant. Because those outer layers are so far away from the central hot core of the star that the slightest bit of outward pressure from radiation can make them drift away from the star and be unbound by gravity. And that's what happens here. We see some shells out here. Daryl's talked about these shells himself as well, saying, gee, maybe those came out first, you know. Well, it could be true, or these could have come out first, and then this happened to be some kind of a high-speed ejection that overtook all those other ones. You know, we don't know the chronology, and that's what makes it so interesting, is that we don't know all the chronologies.
The Gaia mission supposedly spotted the helix at about 655 light years away.
Okay. And as we said, you know, it's notoriously difficult to gauge how far away planetary nebulae are. But I want to show you something. We're going to zoom in here. If we zoom into the middle here, okay, first of all, you notice all this detail. There seems to be some radial detail going out, and there is. All right. I'm going to enhance this a little bit. I'm going to sharpen it up. Watch this now. Okay. Now, look at that. Now details are even sharper in here. This is called an unsharp mask. We're doing it dynamically. And you'll notice the star in the middle here. This is the remnant core, the collapsed star left over from this process. When a star expands into a red giant, okay, the core will also collapse as the star finally runs out of its fuel. The star collapses. It can only collapse so far, though, when it has a certain mass. And that mass has to be less than 1.44 times our sun's mass. And if it's less than that, then the star will collapse to a certain point where the electrons themselves that are separated from the atoms are pushing out with a pressure to hold the star up. And that pressure is called, has a name, it's called electron degeneracy pressure, but don't worry about that. The star is very, very hot. And that heat, 40 or 50,000 Kelvin, Kelvin is a temperature scale, that heat, the hotter a star is, the bluer it is. And if you notice, in this field, there's only one really blue star, and it's this one right in the middle. And that's because this white dwarf, which is about the size of the Earth, and about 600 light years away or so, is still very visible, very hot, very blue. And it's that blue heat, that blue hot ultraviolet radiation that it emanates that causes all this gas to be glowing around it. This is oxygen in here, there's hydrogen out here, there's neon out here, there's other elements as well. So we'll let this one grow for a little bit, then I'll mark it and save it.
This is one of those objects that visually it's hard to see, but it photographs beautifully.
Yeah.
It's big and it's dim.
Yeah.
So it's not easy to see it by eye.
You said you saw it in a telescope once, right?
I did, but it was a great big telescope with a special filter.
Yeah. How much of it did you see? Was it just like a quadrant of it?
Yes.
So did you see?
It was like the lower right quadrant is what we saw.
Oh, this here, that's a brighter one, yeah.
Yeah.
Well, that must look pretty cool. Now, what that means, though, guys, if you think about it, if you were flying in a spacecraft into space and you headed toward the Helix Nebula here, and you're just looking with your eyes, you wouldn't even see it. You wouldn't even see this nebula. You would fly right through it and not even know it was there, because you wouldn't see it. You might register that there's a slightly higher density of the interstellar medium as you pass through here, and you might recognize that the skin of your ship might be heating up a little bit from impacts with these hot hot nuclei actually that are out here striking your ship as you fly through. But it's pretty interesting to watch to think about those mechanics of how heat in the interstellar medium would transfer, because there is no temperature out in space. Things either absorb radiation or emit radiation. They don't talk about them as being a certain temperature. They talk about materials that can be heated to a certain temperature. The James Webb Space Telescope has a sunlit side temperature and a non-sunlit side temperature. But gas atoms in a cloud like this, well, they have a certain amount of energy, right? And that certain amount of energy does translate to a very, very vacuous cloud temperature, so to speak. But that energy gets transferred to your ship as you're flying through it. And so your ship might heat up. This is called a rarefied gas. Very, very few atoms per cubic centimeter in a nebula like this. Considering that there's I think it's 100 million atoms in a cubic centimeter of air. You're down to just a few atoms per cubic centimeter in something like this. But because it's so far away, you can see the overall effect of ionized oxygen atoms, sparse as they are, away from each other.
I imagine if we had a spaceship capable of flying there, we would have a heck of a sensor suite that we could probably detect that.
Yeah.
Planetary nebula ahead, Captain.
Yeah, that's true. And what would we do with that knowledge? Well, we'd say, let's go sit in the middle of it and see what happens. So I think that it's interesting to talk about how that stuff actually works. So again, we talk about these nebulae being made up of these ionized atoms that are now just nuclei. In some cases like hydrogen. But again, the gas in here is heated up in general to what could be millions of degrees. If it's a supernova, it could be millions of degrees. Here, the temperatures of planetary nebulae can vary a little bit depending on the distance from the ionizing source, which is this white dwarf star, which is what this is. But I'll tell you, it's one of those most amazing objects in the sky. Now, we've stacked 18 images. Notice that they don't look noisy anymore. It actually looks kind of pleasant. We can now start to zoom in even more. All right, so let's do that. Let's go and let me move this up in the center, and let's just dive into this for a minute.
They call it the Helix. It certainly looks almost like a corkscrew seen at a slight angle, or it reminds me of like a threaded rod or a bolt,
Yeah.
Where you see the threads in the screw. I wonder at its actual shape.
Well, Daryl brings up a good point, because when we look at the universe, we have to remember we're seeing it in 3D. Okay, it's 2D. It looks like this is a flat donut, right? But a donut's in 3D, isn't it? So how deep is this donut? Is it a cylinder that we're looking down into just by chance? Or is it a spherical set of shells that have been released from the star, only to be seen like this when you see it from any direction you look at it from space? Because it's like this. If you're looking at my hands here, you can see through my fingers, but on the sides, okay, you can't see through my fingers because there's more stuff there. Then on the ends, you can see through my fingers. Well, is that why we see through the center of the nebula more clearly than the edges of the nebula? Because we're seeing the same effect in place. Undoubtedly, that's true for some, because when you have a uniform shell of material moving away, it will always look like a ring. All right, it'll always look like a ring from whichever perspective you see it from. But there's studies to indicate that the ring nebula, for instance, has more depth to it than just donut shape and ring shape, sphere shape, rather. And the helix may also be the same type of thing.
I see this, and it makes me think of a lawn sprinkler, perhaps. But if so, it looks like it has walked over time, you know?
Mm-hmm.
So it's not just concentric, it's offset a little bit with each revolution.
Yeah.
But that's just the impression I get.
Well, we do have to remember, and Daryl knows this, we do have to remember that white dwarf stars don't just sit there. They're rotating. They can be rapidly rotating, and it can be rotating slowly. And that rotation will affect the overall morphology, that is, the way a nebula is going to look. So it could look very, very, very odd. So let's pull this in here. Yeah, there we go. Look at that. That's a really pretty object. Let's move this out of the way too. Very nice. And again, this is the Helix Nebula.
C. Ramos has a question. C. Ramos, I do not know what you're talking about.
That's Claudio. What's he say? Have our friends know something about the AZURE, short for the Auroral Zone Upwelling Rocket Experiment? Auroral Zone Upwelling Rocket Experiment. AZURE is the name of the project, and it's the Auroral Zone Upwelling Rocket Experiment. That's what AZURE means. And I'm not sure. I know about sounding rockets that they launch from Wallops Island and from Norway. I've seen sounding rocket launches and seen what they do when they release chemicals into the upper ionosphere. They interact and they actually create artificial auroras, and then they study how that material drifts over time, and it gives them a great big understanding of these upper air currents plus electrical charges and how they travel through our atmosphere. So if that's what you're talking about, Claudio, then maybe that's what we're talking about here. So I know about those experiments, and there's certain rockets they use to get up high in the atmosphere. We talked about these on one of our SkyTour radios, Daryl, on one of our shows.
Yeah, well, that kind of rings a bell when he describes it.
Yeah. And hello, Donald Kunzer. How are you?
That may be going on up in Alaska. I forget.
Yeah, I know Norway launched a bunch of those rockets, and I know that I do know that we launched them from Wallops Island, Virginia, here in the United States.
Well, you know, if you want auroras, you got to go where the auroras are.
Yeah.
Up north.
Yeah, but I know but it doesn't matter because they want to generate the auroras, and they actually launched off Wallops Island right down in Virginia, and they launched it into the ionosphere, and they released this material there, and the material creates an artificial aurora. Wherever they launch it, it'll create an artificial aurora. It interacts with the very, very rarefied atmosphere up there and the solar wind particles that are in the upper atmosphere. But I saw it right from here, down south, actually, and it was right up high in the sky because it went up so high. I've also seen rocket launches from Virginia, from here in Connecticut. Now, Virginia is, 300 miles away? And it takes about 90 seconds for the rocket to...
Is that all?
I think so, about 300 miles away. And it goes from... it takes 90 seconds for the rocket to clear our horizon from down there, based on the curvature of the Earth.
You're only 300 miles away from Virginia?
I believe so.
I know things are smaller back east, but...
You're funny.
Well, it's closer back there. I mean, the biggest state east of the Mississippi is smaller than the smallest state west of the Mississippi.
Yeah. Yeah, no, I mean, I'm only 200 and something miles to Washington, D.C. So.
I don't shoot.
And to Wallops Island, a little farther south, I'm just guessing about 300 miles.
It was launched in Norway. Auroral Zone Upwelling Rocket Experiment, or AZURE mission.
Yeah, I saw the results of that mission. They made four spots in the sky. In fact, I received it as a UFO report, and quickly contacted the folks that do the AZURE missions, and they actually said, "Oh yeah, we launched an AZURE." So, okay, that's
Black Brant. Where sounding rockets were launched. Blah blah.
Yeah, Black Brant's the rocket of choice.
Yeah, studying the energy exchange within an aurora. And here's a neat picture of it. Perhaps you'd like to share this, Mark. I'll post a link in.
Do it in our chat, because if I click on the chat in the broadcast software, it's gonna screw up the chat, and I won't be able to read the chat anymore.
Okay, so you want it in your chat?
Yeah.
There it is.
Okay. Yeah, that's what I saw.
Cool picture.
Yeah. All right, this is what we're talking about, guys. Whoops. Sorry about that. That was from the other day. We don't need that anymore.
It's trippy look.
Yeah, it was. Yep. This is based on the materials that were released by the rockets. These are the launch plumes left behind as the rockets went up to altitude. They released two separate sets of compounds in the ionosphere. And Black Brant is the name of one of the rockets. They're the rocket of choice. Pretty cool.
They've been seeing some blue aurora-like things up northern Scandinavia recently, and they say they're from Russian ICBM test launches.
Mm-hmm.
There's something kind of unique about them.
Wow.
That was a cool picture.
Yeah. Well, there you go, Claudio. And that's the end. That's the answer about AZURE. All right, we've stacked 36 of these. We're going to stop now. So let me bring back my telescope view here. There we go. And now we will remove the name, because you don't need to see that anymore. You know it's the Helix Nebula. All right. And then we can save this. I have Helix Nebula up here, and you're going to see the Helix saved to a directory by that name.
Can we zoom in a little bit before you leave?
Yeah, we're not going to go yet.
All right. We're just barely catching some detail on this thing. The radial structures you mentioned.
Yeah, you can see a lot of it here.
Cometary globules, I think they call them.
There's one right there.
Yeah, they're not really comets. They just have a comet-like kind of look to them.
Yeah, the star is evaporating material because it's so powerful with its radiation. You can see it's looking radial. You can see the radial spikes here. That's not an artifact of the photo. That's actually real. That's in the object itself.
Really cool picture.
Yeah, looks pretty. All right.
I've noticed lately when we looked at this, we used to see some faint nebulosity to the lower right, like what we see at the upper left.
Well, I only did a 30-second exposure, and I think we might be able to see something here, but let's actually do this. Let's pump it up really hard. Okay, don't worry. These diagonal streaks are an artifact in the camera that we're fixing. I think this is it right here, Daryl. See it?
Yes. Oh, yeah, I see that. Barely, but I see it.
Yeah. But that's really pretty, guys. Very, very beautiful nebula.
Some people call this the Eye of Sauron.
It looks like it, doesn't it? It looks like the Eye of Sauron. Don't you know? Okay, so we'll save this now. We're saving the raw FITS file, an astronomical file format that you can look at with a free viewer. And then I'll save it exactly as you see it here as a PNG or a PNG file that you can just simply double click on. And where is it being saved? It's being saved to our server, which you can reach by going to SkyTourLive.com right here and scroll down to the gray section next, and it'll say take me to cool pictures. And you just click on that link, follow the instructions right there on that screen, and you can dive down into the directories and take those pictures in seconds, and they're full resolution, so you get them as they appear here. Alright, so there's the helix, and we'll clear this and move on to the next. Okay, and we're going to go into our night vision mode in 1 second intervals.
Are we doing the southern sky tonight?
What do you mean the southern sky? I mean,
we've been spending a lot of time in the northern sky lately, you know, Cepheus and Cassiopeia, all that.
oh yeah, well, we can.
Just wondered, you started off here tonight.
I did, and so we might be able to catch the Sculptor Galaxy, right?
That's what I was thinking.
Were you?
Yep.
253?
Yep.
Okay, let's go see. Let's see if we can find that. Well, I know we can find it. There we go.
Might be a little early.
No, not really. It's not far away. It's right. I had Diphda in here just earlier.
All right.
So let's go to this guy. This is a beautiful galaxy which has the most incredible shape to it. If you watch,
just about on the meridian, in fact.
Yeah, if you watch the telescope right there, you'll see that it's heading in a very pleasing direction, above the wall of the building and to an area that shows us this beautiful galaxy. Now we're talking. All right, the telescope's going to stabilize, and we will get our guiding system online here in just a couple minutes. Not even a couple minutes. It's going to take 14 seconds from once I stop moving it. Okay, it'll take 14 seconds to get our guide star. When you'll see a guide star, you'll know it because this will go from searching to a zero initializations for all. It'll 0000. You'll see it in just a sec. Like there it is, and then it's going to start guiding. All right, so we'll let that stabilize. Meanwhile, I'll say hello to Mike Hedrick, who's here. Hey there, Mike. Good to see you. And who else did I miss? Did I miss anybody? I don't know if I have. I don't think I have. Interesting. All right. So now what we'll do is we're at 400 sensitivity here. That's what this indicator is over here. That's about. Oh, look at that! A little satellite moving through the field of view. See that? Right there.
Yep.
Glad I waited because. And there's another one that just moved through at the upper left, right there.
Yep.
Yeah, that one's probably a Starlink. This one's not. That's some other rocket body moving on a north-south trajectory.
This galaxy is about 5 times as far away as Andromeda is. If it was at the same distance, it would look at least as good as Andromeda does.
I think you're right.
Called the Silver Dollar Galaxy.
Yep.
Sculptor Galaxy. Intermediate spiral. I believe it's very dusty.
Yeah.
And it's a starburst galaxy undergoing intense star formation.
Right, and when we zoom in on it, you can actually see the areas that are redder than the other areas. This nucleus is quite orange. You can see it kind of now. But let's let's do a exposure of this for 35 seconds. All right, and off we go, and then we're gonna come out of our night vision mode and go right into our live stack mode. All right, so our live stack mode is here, and we have it so that it's not interfering with the image. So we'll see that in just a sec. So let's wait and enjoy this coming in.
It is smaller than the Milky Way.
Mm-hmm.
It's only about 45,000 light years in diameter.
Compared to our 100,000. Compared to our 100,000, man. Look at that. Now that's a beautiful galaxy. Look at this. So now we only have one image in here. We're about to stack a second. All right. And as it does so, this trail is going to get long here. This is a satellite going through the field. But galaxies are interesting because out in the spiral arms, which are out here, right, away from the nucleus, you'll notice that they're distinctly bluer. Well, that blue coloring is due to the fact that there's star formation going on out there. And then inside the galaxy's central area, these are the older stars. They tend to be yellower. And in galaxies where there's new star formation, you'll see a decidedly and markedly bluer set of spectra coming from this galaxy when you look at it in the spectra. And those are mostly the spectra of young hot stars. Like, look at all these blue ridges here. There's a lot going on in here. Right, so watch the noise change a little bit now. Okay. All right, so now if we come in here, let's see what it wants to do. Okay, so see, it wants to go a little too far in my estimation. So I'm going to change that processing a little bit to make it a little bit more proper. Then I'll do a color correction, and you'll see the space turn more black. That's a good coloring. You'll see all these knots. Okay, these knots of areas in here, these are H2 regions as well. That is to say, the red regions that we see, like our Orion Nebula, Lagoon Nebula, where star formation is occurring. So there's a lot of those in this galaxy as well. Dean Bostador and Tim F, how are you guys? Good to see you. Dean Bostador asks a really good question. How can you tell if something on the screen is a satellite or a meteor? Very good question. A meteor is a transient event. It happens usually very quickly. And when it happens, the way a meteor tracks into the atmosphere, you'll see it gradually get brighter. Then it reaches a peak, and you'll see a flash. And that's usually where the meteor explodes as it reaches its maximum capability to withstand the atmospheric pressure. And then it trails off rapidly. So meteors have a characteristic trail that's a little bit of a gradual increasing streak followed by a bright burst and then a slight tapering off later. That's a typical meteor burst. Satellites are a constant trail that you see. They tend to fade in and fade out rather slowly, and they go further distance than a meteor generally. I mean, there are meteors that cross the entire sky, but they're somewhat rare.
Meteors tend to move much faster.
Yeah, but if we're talking about a photo, you can't tell how fast it was moving. But yes, if you're looking at it with your eye, the meteor is instant, and you could call someone on the phone and say, "Hey, look up in the sky now. There's a satellite passing by," and they'd be able to see it, right? But a meteor, you can't do that with, as Daryl says, because it happens too quickly. Hello, Militia Schmidt. How are you? Yeah, there's no pressure per se, capital P, in space. You can have pressure inside stars because that's not empty space. That's dense gas. You can have a semblance of pressure inside of a nebula that's compressing, and from gravitational contraction. But the thing is, you don't have a true pressure, with interstellar space. There's so few particles. Remember, the definition of pressure is what the particles in a contained volume are doing, right? In terms of their motions. And when we look at space, the contained volume contains so few particles that a discussion of pressure is not even significant. But it's a very good question. Thank you, Melissa Schmidt. Or Smith, I see. I'm sorry. Well, no, yeah, that's true. Daryl let you know how far away the galaxy is. And think about this. Is that what the question was? The distance to...
He asked how far away it is, and it's about 11 million light years away, and he said that's far. And
oh, right, okay.
I said that's not far as galaxies go.
Okay. Yeah, I mean...
When we look at the Virgo cluster in the springtime, those are all 50, 60 million light years away or more.
Oh, yeah.
And we see them a whole lot farther than that. When we see young galaxies in the Webb images, for instance, the Webb Space Telescope, those things are like billions of light years away.
Yeah. And they have something called the cosmological redshift in play, which means that all of the light coming from them, see, we're seeing this in visible light. We're seeing this is what we could see with our eyes, right? But if this galaxy was farther away, it'd be moving faster away from us. And the light we're seeing now would actually be shifted toward the red end. That's called redshift. If it was coming at us, that light would be shifted toward the blue end, so the galaxy would tend to look bluer. This galaxy would be a good example of one. If you could put it far, far away and accelerate it away from us, like many of the galaxies at a far distance, then the visible light we see here would actually end up being shifted into the infrared. Okay, because you go past the visible spectrum and go into the infrared, and move fast enough and be far enough away, and that redshift can bring you so far into the red end of the spectrum that no telescope you have could ever hope to see it, because you need to have an infrared telescope, and thus the James Webb Space Telescope was born for that very purpose, was to look for galaxies so far away, moving so fast that all of their light is shifted very far into the red end of the spectrum and into the infrared zone. The Hubble Space Telescope could see a little bit into the infrared, and it's taken infrared images of galaxies far away. But the James Webb is much bigger. Okay, it's 21 feet across in terms of its mirror versus 8 feet, about 100 times better than the Hubble Space Telescope. And it can see a lot farther into the infrared because its sensors were built for just this purpose. And it's nice because the James Webb Space Telescope can also see the atmospheres of exoplanets around other stars, which is a very cool opportunity for us as well. Michael Hedrick has a question.
It's a mighty big question, too.
Can you talk about the different properties of nucleus of different types of galaxies in terms of ages, density, etc.? Well, okay, at the very least we can say this. In many galaxies, the reason they may be galaxies at all is because they've been seeded by a very massive object. In some cases, we've identified those, like in Messier 87, like in our galaxy, a location called Sagittarius A. And Messier 87 has a supermassive black hole that we actually imaged for the first time using the Event Horizon Telescope consortium. Multiple radio telescopes looking at it all around the world, which basically made like an 8,000 mile diameter telescope looking at it, which gave us the resolution we needed to see it. Same thing for Sagittarius A star, the center of our galaxy, which has a supermassive black hole as well. So It seems that galaxies will have and do seem to have supermassive black holes at their centers. Some galaxies, after being in collision with other galaxies, may end up with merged black holes from two galaxies merging. That's something I had been looking at some studies about that too. And when they do merge, they tend to release gravity waves. And we see that, we detect that, and say, hey, what was that? And we look in that direction, and then we see a very, very odd event going on typically. Merging neutron stars, or merging black holes. The gravitational waves released are very interesting because, Einstein, I don't think he felt that we could see gravitational waves until we did. So it's there's a lot of interesting finds going on right now.
Some galactic nuclei are relatively quiet. Some are extremely busy. This galaxy is undergoing starburst. A lot of rapid star formation. Somebody mentioned the other night a well-known galaxy we haven't seen a black hole, supermassive black hole in. Was it M33? I forget.
The Triangulum Galaxy?
Yeah. I don't remember. It may have been it. I want to say Izabela mentioned that. I could be wrong though.
Okay. Yeah, I don't remember that. Daryl's looking it up, you can tell.
No, I'm not.
Oh, I hear you typing, so I thought you were.
I was saying hi to Cindy.
Okay. Hi, Cindy Murphy.
Like I said, I mean, that's a great big question. It'd take a half an hour to answer that.
Well, and it's only to the best of what we know right now anyway. So, here's a little better view of this. Nice detail in here, isn't it? Okay, we stacked 20. I think that's good for this one.
We zoom in on it?
Yeah, we will. I'm going to save it first. And save it exactly as seen. So this will be up in the database before long. Alright, let's check it out now up close.
There's a lot of dust in that galaxy.
Yeah, look at all the dark black dust. This black dust comes from countless supernova explosions and from the atmospheres of red giants. In the outer atmospheres of these stars, they're so big and bloated, like Betelgeuse and Orion. If you put Betelgeuse where the sun is, its orbit would go out almost to Jupiter. So way out there, that gas is not really held very well to the star because it's so far away. But also out there, you can have molecules form in the outer atmosphere of the star, and we literally can get like a carbon-carbon molecule formed out there in such locations, and because it's so cool, it's not hot by stellar standards of millions of degrees or so. So when we have a carbon-carbon molecule out there, it means that that's like a little tiny particle of soot, and we could get a lot more that way too, and sometimes we do. Sometimes they create particles made up of all these carbon molecules, and we end up with an interstellar particle of soot. And in addition, the other particles we see out there come from other materials that are made in the hearts of these big stars, and that's silicon. And you get silicon particles out there, and they conglomerate, they build larger particles. And as I've mentioned last night and the night before, ice forms on these particles. And this ice can be methanol from aldehyde, water ice, carbon dioxide ice. You have cyanogen, cyanide, that can also form on there. And you get all these compounds which form on these little particles of dust. And then that's sort of like the chemical factory of materials needed to build a planet And if there's any hydrogen in this cloud as well, then the hydrogen gas can be used to make a star.
If you look at the ends of this galaxy, at the upper left and especially at the lower right, kind of reminds me of what we see in M31 Andromeda, especially the one on the lower right, that big, huge OB association, or that extra bright patch right there.
And then this one. And then this one. Yeah.
Very prominent in Andromeda.
Yeah.
Maybe we're seeing a little bit of that here as well.
Well,
But they say it is an active star-forming galaxy.
Yeah. And that could be because of the many hydrogen gas emission cloud regions, which we call stellar nurseries or H2 regions. Hey there, OG Skywatch.
OG, I think they're a good choice.
Well, let's read his question.
Our G-type main sequence yellow dwarf stars like our sun, the most likely to support life, might narrow the search for exo-life. They're a relatively good choice. O and B, the hotter, bluer stars, are poor choices because they're so hot and such energetic radiation. You're probably unlikely to find life there. And UV, yes.
So I think the other stars, though, that we're looking at right now with a particularly keen interest is the most populous star in the universe, and that's the M-type star. You have O, B, A, F, G, K, and M. G, of course, that type is our sun, and we found that life can exist on a G-type star because, hey, look, we're here. Ta-da! Okay, but that G-type star also has ultraviolet radiation it gives off, which gives us skin cancer, and we are on a very tumultuous planet, which can kill us from earthquakes to tidal waves to volcanic eruptions to climate disasters. The planet has its own issues, and so it's not what would be called a super habitable planet. It's habitable, yes, but not super habitable. It's really not the best place for humans, but we're here in spite of it. So, and that has to do with the G star to some extent. But the M-type stars, those have more planets around them than any other type of star in the universe, primarily because there's more M stars than any other type of star in the universe. So it's pretty interesting. Right?
Sure.
So
NPC1, I saw your question, then you retracted it. I don't think stars could live in that short a time frame, but the really bright, really hot stars can live only millions of years as opposed to billions of years for smaller, colder, cooler, dimmer stars.
What was this question for everybody else?
He asked, I think it was, he retracted the message, could stars live like 10,000, 40,000 years? They'd just be starting getting rolling at that amount of time.
Yeah, I think that you're talking a few million years for the biggest stars. As Daryl said, the O-type stars, those are the big boys. Okay, and those would go through their hydrogen and vanish in a cataclysmic supernova explosion. I don't think there's any O stars that won't generate a supernova when they run out of, their fuel. Finally, I should say, because they'll take some time. Okay, we got 31 of these stacked. We're gonna save it here. I got it set up there so I can save it.
Very nice.
Pause this. We're gonna save it, and then save it exactly as seen. Alright, we'll clear it the next time we come in. It'll stay in the buffer. And we're going to go back to a 1 second night vision shot. And we got to get rid of the stack.
Can we see the flaming star yet?
Maybe. If you remember, we looked at it the other night.
Was that in Auriga?
Yeah.
Yeah. Oh, Daisy and Zoe asked about the flaming star and the horse head.
Okay.
They put them both together, and I wasn't sure which flame nebula, whatever she called it, was, but said it was with the horse head.
Maybe they're saying the Flame Nebula. They're saying the Flame Nebula, not the Flaming Star.
Yeah, okay. Yes, yeah, the one next to Pound Attack.
You got it.
And we won't see those for a while yet. Orion, if it's even up yet, it has to get high enough to see over the wall of the observatory before we can see it. Later in the evening or later in the year.
Yeah. I mean, Orion's up now. It's in the east-southeast right now.
There.
But it would be just a little bit difficult for us to see because we'd be looking through the wall of the observatory here to see it.
Yeah. But hey, it's getting up earlier and earlier every night. We'll be able to see it here. I don't know if I plan to stay up late enough to see Leo rise again, but
no, I'm actually
Orion will be well up fairly early tonight.
Yeah, no, this stream is not going to be one of those 4 and 5 hour streams. We're going to be, actually, we're an hour and 3 minutes into this one, right? Just about.
Something like that.
Yeah. Now we're going to check out a couple more objects, a few more objects, and then we'll call it, because this was a whim. I wasn't even sure I was going to do this stream. All right, we're going to go check out the Triangulum Galaxy here. We might as well.
Sure.
Because it's right up. We're going to be looking almost straight up at it. Almost straight up, not quite. And when you have objects that you're looking straight up, you're looking at them through what we call very little air mass. And so they will look better. And there it is right there. They will look far better than you may see them otherwise. And that's because you're looking through the least amount of air. So when we look at this, we're going to definitely see a much more beautiful object. I will just check the focus, which I'll zoom in real quick and see, just do a visual assessment. Make sure we're looking good. Yeah, it looks pretty good. All right. So let's bring this nebula toward the center.
Hedrick, I think it was Hedrick, wasn't it? Was asking about galaxies earlier. What you'll see now, this is a very different sort of galaxy than Indice 253 was.
Yes, indeed.
Well, this one's face on for one thing, but this is a very loosely wound spiral.
Yep.
And it's a different sort of a galaxy.
This one's called an S, capital S for spiral, and then a capital A, and then little c. So this is by the new galactic classification scheme. It's effectively an SC. There's SAs, SBs, SCs. Those are all, the second letters are always small letters. And it's either going to be, with the new classification scheme, the spirals are specified to be capital S, capital A, or capital S, capital B. And that's because they noticed that many spiral galaxies also have qualifications and qualities that liken them to barred spirals, where the nebula, the nucleus is a little extended, and the spiral arms come off of that. This is not one of those galaxies, but it's called an SAC type galaxy. C meaning loosely wound arms, B meaning more tightly wound, like Andromeda Galaxy is a B type winding. Our galaxy might be a C type winding, maybe a B type winding. It's hard to tell because we're actually inside the forest. We can't see what our forest looks like from the outside.
I still wonder that they can tell that we are supposedly a barred spiral.
Yep, that's what they said. Okay, we'll do a 35-second exposure. We're guiding nicely over here and stable. Let us go see. And we'll come out of night vision mode. We'll come in here. And I left this one in here primarily because we're going to now see what a galaxy looks like face on. Here you're seeing a galaxy kind of on a sloped angle, kind of a low angle, right? And now you're going to see one that's face on, just facing us like this. So that's the difference between these, and that makes a huge difference. It looks beautiful. So let's clear this now. This is in the image buffer, so now that it's clear, it's going to read off the image from the chip. And here it comes. Here we go, and let's actually process it. Look at that. Okay. You can already see the spiral arms in what amounts to be just a 35-second shot. And the reason we stack them is because there's noise. Like you see this mottled area in here. I'll just show you here. We'll zoom in here. Okay. See all this mottled color in here? Watch what happens here in a couple seconds, right? We have 3 seconds, 2, 1, 0. Watch the noise. Boom. It's knocked down. And with successive exposures, it's going to get knocked down more and more and more. And so the noise is random and will be averaged out over time. And all the detail in the galaxy will be thrust forward, and we'll see just a very beautiful galaxy after all this.
I didn't see it do anything.
It did.
You still have unsharp masking on?
Yeah, no, it did it. Yep, it did it. Watch again. It's less on the next one. Okay. Okay, I know you didn't see that one either, but it did it.
Actually, I did see that one.
Okay.
Sort of.
Okay. So now, what we can do is we can play with the settings here and tease out some more data. So let's add some contrast. Let's darken space up behind the galaxy and around the galaxy, and add some contrast to those arms. Look at that. So let's check that out. Okay, so now you see that. Down the bottom here, you see this green area, right? Well, if you come up here, there's another green area here, another green area here, right? Another one here. And throughout the galaxy, it's dotted with little green areas, okay? These are areas where there have been supernovae. And just like with the Veil Nebula, supernovae have extensive oxygen ionized clouds of gas, and so we're looking at supernovae in this galaxy. All right, and also you'll see this guy right here, right, and this guy right here, and various others like it. Those are H2 regions, and because they're so prominent, they have their own names. This is what, NGC 604.
Yes.
Right here. I don't remember what this one's name, but it has a name.
There's a bunch of NGC objects inside M33.
Yeah.
604 is the one I remember offhand.
Okay, we can find out right now because I think that they'll be here. Okay.
There you go.
So we have 604. And this guy is 595. So we have 604 right here and 595 right here. And then we have these guys, which are the supernova remnants right here. This guy, that guy. And what's neat is you can see detail in these. And when we start getting more exposures in, we can start zooming in more and checking these out. You can see looping structure in here, which is really cool. I'm going to take off the detail enhancement here for just a second. Let's check it out. Okay. So now without the detail enhancement, you can see some of these structures actually a little better.
Some a little worse. I was looking at the bright spiral arms, and
Yeah.
when you turned off unsharp masking, they got dimmer.
Oh yeah, that's true. But I was just showing what can happen.
Yeah.
Yeah.
If you look at them now, there's one spiral arm up above at about 12 o'clock, pretty close to the center, and then one down below. And how distorted the bright blue spiral arms are there, just above and just below the nucleus.
Yeah.
See, they're not smooth curves. They're all sort of ups and downs and wiggle woggles in them. And
Yeah. Well, that could have been from some type of gravitational interaction with the Andromeda Galaxy, which is actually right nearby,
Yep.
physically in space. You know. So this is like 2.7 million light years or so, I believe. I have to check that to be sure. I can just check that right now. For this guy, it may not be correct, but let's see. Yeah, this is 2.72. Not sure if that's accurate with current findings, because we've had issues with distances. They change because of better formulae, better data to calculate distances shows up, different techniques, and so forth. Hey, Uber Crew, how you doing? Question: is there a reason why each of these green supernova remnants are majority green? Is that from similar star compositions or scale of the explosions? Actually, very good point. I'll tell you why. This is what we think. First of all, if you look at the elemental abundances in the universe, hydrogen's number 1, helium's number 2. Guess what number 3 is? Oxygen. Okay? And number 4 is carbon. Well, of those, which ones glow when they're ionized? Hydrogen glows red, and oxygen glows bluish green. Okay?
Yeah.
So we're going to tend to see, in any kind of gas clouds, we're going to see an abundance of oxygen and abundance of hydrogen. And here we see abundance of hydrogen causing these beautiful H2 regions, and here we see abundances of oxygen. So it comes from the elemental abundances in the universe, and that comes from how stars make these components, make these elements in their nuclear furnaces. And then other stars get made from them, and when those stars go supernova, they release them, what they were made with, that never did anything but sit as plasma in the outer envelope doing no fusion, and they get released back to the interstellar medium.
Now, didn't we see the other night, can you zoom out or drop down toward the bottom? I thought we saw even another, okay, maybe
I
that
think
must
that
have
was
been
it.
then. Yeah.
Yeah. Donald Kunzer asks
Pretty far out in the outskirts.
yeah, pretty good question. He says, trivia question. Of this galaxy, Andromeda and Milky Way, which is the largest? Aha. Okay, between this galaxy, Andromeda, and the Milky Way, Andromeda is by far the largest. Andromeda has over 1 trillion stars in it compared to our 100 billion. This guy here, I don't remember exactly what its size is. It may be smaller than our Milky Way or larger, I'm not sure.
It's smaller.
Okay.
A lot of people say Milky Way has about 400 billion stars now.
Well, yeah, I've always said 400 billion, and that 10% could be Earth-like planets around those stars, and if you look at the statistics. But then I kept getting poo-pooed by so many people saying, well, we don't know that for sure. So I've always said between 100 and 400 billion. In my book, I say between 100 and 400 billion. But we can't stand outside our forest and get an accurate count of the stars. Oh, we can count the stars in this galaxy. We can count the stars in the Andromeda Galaxy. And it's a statistical counting. It's not a direct counting. 1, 2, 3. 427,301,000. Oh, no, I lost my place. 1, 2. It's not like that. But it's a statistical counting. But,
The current mass of the Triangulum Galaxy is 50 billion solar masses, so
yeah.
And they say 40 billion stars.
All right, so when you think about our galaxy, the low end estimate is 100 billion stars for our galaxy. That's always been, the low end, and the high end has been 400 billion. So, if you want to estimate, you can say, all right, we have 200 billion stars. That's probably closer to the right answer than 100 or 400. But the fact is, when we talk about the number of habitable planets in these galaxies, based on what we see so far, and the number of super-Earth planets that could support life potentially because of their mass, not necessarily whether they have atmospheres, because we don't know that yet, it could be approximately 10%. So, in other words, we could have 10 billion to 40 billion other Earth-like planets just in our galaxy. And if you have a galaxy that's so much bigger, well, guess what? Your chances have just improved for finding life. It doesn't mean intelligent life. It just means planets that can support some type of life. And Mars could be one of those planets that can support some type of life. The moon Europa around Jupiter could be one of those moons that could support some type of life deep in its oceans. So we have to define life. Intelligent life? Well, now you have to narrow that funnel a lot more. There's a lot of hurdles to get over to get to intelligence.
I think the unsharp masking really helps in 33. It really brightens up the spiral arms.
Yeah, here, let me show you. I'll take it off so you can see what it does. So we turn it off, right? And it helps us see the nucleus if we keep it off. Turn it on, and because of the density of objects in the nucleus, it gets a little bit overexposed. See that?
Oh, I think that's nice.
Well, I mean, it does look nice, but you can't see the detail until you do this. Now you can see the details in there. See? But this is what we get in the data when we take the data. And then it's up to us to process that data to make it look better. This is an on-the-fly processing that we can do, which I love. I mean, it's just beautiful.
Oh, the unsharp masking brings out all that fine detail in the spiral arms, though.
Yeah, it does. It does. But that's not going to end up in the astronomical fits format file. We have to do that all ourselves if we're going to do the processing. This is just the on-the-fly stuff for the saving of the picture as it is on the screen. That's where you would actually, where you benefit from it. It'll stay there, but it's not going to be in the raw file. So, all right, so if I say save right now on 21 stacked, we'll say save. Okay, that's our astronomical fits file right up there. That isn't going to have any of this processing on it at all. We have to draw that out and start bringing this processing out. That's a manual process to do that. But then I say save exactly as seen.
Which you always do.
Yeah, right. But I'm just pointing it out for everybody. Save exactly as seen. This gives you this image. And if I was clicking on this, okay, if I just click on that, here in the program, which looks at these things, here is the full res image of the Triangulum Galaxy as produced by the camera. This is what you get on the database. And you can zoom in on it. If you have a program to look at this, you can zoom in on it and, see cool things, right? And just have a lot of fun checking it out, right? If you need to know what program to use, I can certainly help you with that. I teach people all over the country about tools like this to use to analyze photos and have some fun looking at pictures. So I'll be happy to help you with that. If you want to ask me a question, you can contact me through SkyTourLive.com and pass either of us questions if you want. And it can help you all out. OG Skywatch says, Thea theory. I think that you're talking about the impactor that created the moon in the beginning. Is that what you're talking about? Hello, Lewis. Lewis is with us. Lewis Todd. Lewis Todd says, used to have a human population until ET nuked it. I think he's talking about Mars, maybe? Not sure. UI Scooty, is that visible? No. I don't think UI Scooty is going to be available to us until the summertime.
Yeah. It's same constellation as M11 Wild Duck Cluster. It's above Sagittarius, and it's well down now.
Yeah.
Sagittarius is setting right after sunset.
Yeah, we don't get to see that anymore until next summer.
Yeah.
Yeah. Yeah.
Well, I think that's a very pretty picture right there.
It is. Okay, so we're going to stop now, do one more save. So we'll pause this. And this is 26 stacked images. We're going to save it. And save it exactly as seen. So this very picture you're looking at, you can go grab in probably about 45 seconds from now. Again, go here and then go scroll down one section to the gray section. It says take me to gorgeous pictures, and the folders will be by date. And you just go into the date, you go into the folders until you see a folder marked processed. It's called processed. You go in there, you'll see the picture, and then you can download it and take it down. Look, it's a little work, but you know what? That's available for you. We're working on databasing thanks to Robin, our DB girl, database girl. She actually is creating a database of all our observations. It's finished, and we now have access to seeing our all the work we've done over the last year and some odd. And we're working on a front end to that too, so that all of you can search and say, find me every one of the times you took a picture of this, and show me every time you take a picture. I want to see that picture. So we're working on that. Yep. By the way, Marianne with SkyTour LiveStream, she's one of the people, the movers and shakers that makes it all work. Marianne just got back from southeastern Arizona, where she went to look at a potential land for SkyTour LiveStream number 3, observatory number 3. So very good progress made on that. And I'll tell you more when I can talk about more. All right, so this guy is done. So it'll be up on the OneDrive, our live server for you, in just a few minutes, if not even a few seconds. So let's get out of this. Let's go to 1 second again. There we go. And now we're in our night vision mode. Right there. Okay. Let's back out a little bit. Okay, a little too far. There we go. Alright, so let's back off of this now.
I bet you go to M32 next.
Measure 32 or 31?
Well, you might as well go to 31 while you're at it.
I guess, right? Might as well. Since you talked about those wonderful hot blue associations of stars, I guess it's probably a good idea to show them. Michael says, sorry, I had to step away. Marc, can you tell us what you believe Mars' atmosphere used to be like and how long ago it was different? That's a very good question. Mars lost its atmosphere billions of years ago. I mean, billions with a B. It's like, well, wait a minute. How could that be? Well, Mars used to have a magnetic field, but it lost its magnetic field when the core of the planet ended up cooling enough so that the currents generated by molten material being moved around in that core stopped happening. Because that's what generates our magnetic field, is the solid inner core and the outer molten core moving around it generates electrical currents, which in turn creates electric fields, because electricity and magnetism are tied together forever and ever. In fact, light is an electric field and a magnetic field moving perpendicular to each other like this. Okay, that's actually a propagated light wave is made of that. So When Mars' core began to cool, it didn't have the ability to make these electrical charges as well, and the magnetic field that was generated by those electrical charges ended up waning. So Mars lost its magnetic field, again, a couple billion years ago, and it had a much thicker atmosphere. It had clouds, it had water on the surface in standing lakes and ponds and possibly even oceans. But then, as time went on, it lost the magnetic field, and then when the water would evaporate, well, then the ultraviolet radiation that was hitting Martian atmosphere could penetrate the atmosphere and not be shielded and spirited away, okay? And the solar wind coming from the sun could go all the way to the ground, and thus the ultraviolet energy in a now thinner Martian atmosphere could reach the surface, and the highly charged solar wind coming from the sun didn't go circling around the poles and get trapped in a magnetic field like on Earth. And so the Martian atmosphere ended up thinning, and particles reached the planet's surface, sterilizing the surface with ultraviolet energy. And that also did something very special to the water molecules that were in the atmosphere. It split the H2O up, and you ended up with the molecule of hydrogen, H2, and then you ended up with the oxygen and separate, and that ended up diving down into the ground where it bonded with iron compounds. So Mars is...
And hydrogen drifted off into space.
That's right. And so the oxygen itself ended up bonding with the iron compounds in the ground to make a compound called Fe2, two iron atoms, and 3 oxygen atoms, Fe2O3, otherwise known as rust. So the color of Mars is because it rusted. Interesting, isn't it? Mars, the red planet, is red because it rusted. And that happens here on Earth too. But for us, we have a magnetic field. So that solar wind is trapped by the magnetic field. And it ends up being trapped in our magnetic field in such a way that it confuses people, because they hear about the Van Allen radiation belts and they think that's a separate thing from our magnetic field. It is not. It is there because of the magnetic field. In fact, it is the magnetic field, just made visible because of the charged particles that are trapped in it. And that becomes our Van Allen radiation belt. So it's our magnetic field, and it fluctuates in size just like the magnetic field based on the solar activity of the sun and how that happens. So it's very interesting.
You can see in that 1 second exposure there. Right there, what I was talking about with the other galaxy.
Yeah, I'm going to move it up just enough.
Looks sort of analogous to that.
Yeah, I'll move it up just enough so we can get enough of the upper part. I mean, it goes off both ends of this screen, but you know what? Let's just try. We'll do a 35-second exposure again. But we're going to stop searching until we connect. Notice where we're looking. We're looking straight up almost. This will be the best we can possibly see this, as long as there's no wind. And Daryl likes to let everybody know, which is true, that it's not just the Andromeda Galaxy we see here. We see these other 2 galaxies. And these are, of course, known objects themselves. This is Messier 32, and this is Messier 110. But I like to mention about this galaxy, once we see the images, you can see the dark dust in this galaxy already, just a little bit, in this 1 second shot. But we're going to look up in this galaxy too, because it also has dark dust, which is very rare, because ellipticals don't usually have a lot of dust at all. Alright, so let's go check it out. We're going to go and let this exposure start. We'll go into our live stack. And here we go.
Excuse me a moment, please.
Sure. Cyclone says, I got good news. My brother's not going crazy tonight. No more screaming. Well, that's cool, man. Yeah, Daryl's right. If you're asking a question, you can put your question in caps. But if you put your regular typing in all caps, it attracts our attention, making us think that we have to pay attention to something. But in your case, you were just making a note about something. So you can put your questions in all caps. That helps us. All right? That way we'll see them. Okay, so here is the Andromeda Galaxy, and down here, right there, is this beautiful association of hot young stars that are being made, or that were made actually, and they're probably filling this whole region with copious ultraviolet radiation. You can see there's a bunch of them here. We'll zoom in. Let's just zoom in a little bit on this. There we go. So you can see there is a bunch of them right here. There's more here. There's a beautiful association here, and here, and here. So the Andromeda Galaxy has its share of blue spiral arms with blue hot young stars. So very nice. And the same is true at the top. And it's right here, but I had to let it go off the frame right now, unfortunately. But we only have 3 stacked, so it's going to get better and better and better as we move forward. Oh, I made a mistake on the last one. I named it wrong, but I'll name it right when I get to the place out there. Hey, Dan Norton. No, sir. You can check us out, and we'll show you the heavens and tell you all about it. All right, so this is Measure 31, the Andromeda Galaxy. All right, and I'll make a note of that. All right, and let me fling that name out there for you to see. There we go. Who has more spirals, the Milky Way or Andromeda? Good question. I think the Andromeda Galaxy has more extensive spiral structure because it's a much bigger galaxy than ours. But I think we have, a number of spiral arms, which you can look up online and see. We have the Norma arm, Centaurus arm, Sagittarius arm, Cygnus arm, Orion's spur, Perseus arm. So we have a few arms of our spiral galaxies, our spiral galaxy. But Andromeda is going to have longer ones of its own because it's just much bigger than us. Much, much bigger. Which is kind of cool. And of course, this galaxy is heading right for us, as some of you know. In like 2 billion years, it's going to reach us and pass through us. And when it does, the nature of our structure is going to change forevermore. Yeah, OG Skywatch is correct. And the closest thing to us is the Orion spur. That's why Orion looks so bright, because those stars are relatively close to us, only about 1,500 light years. Daryl just mentioned that. Zoom in on this for a bit.
Yeah, you can kind of see hopefully what I was talking about with
Right there?
the other galaxy. Yeah, that or that whole end of the galaxy, that whole bottom right hand end of it.
Yeah, it looks really pretty. There's one out here that's especially nice. Look at that. See that? Let's see if we can bring out a little more detail here. Okay. And then bring this in. This is called a push. All right. Interesting. You can see more detail when this happens, when you do this. And the more we stack, the more this noise will go away. I want to also show you something else. Up here in this galaxy, you'll notice that this galaxy is an elliptical galaxy. Elliptical galaxies tend not to have any dust, okay? But this one seems to have some. It seems to have a curve of dust in it. Interesting, because that's something that we've never seen before until they started getting better images of the Andromeda Galaxy. Louis Ta says, are those two blue glows the supernova? Are you talking about these, Louis? These blue glows? These are stars that have formed here in what's known as an OB association, O and B stars that are associated with each other. If you see like just blue streaks in our data, that could be like an errant pixel or something. Like right here. Okay, that blue pixel right there is a artifact of the camera sensor. So that's an artifact. Right. And they're kind of random. They come and go.
Just for purposes of comparison, like right there, is unsharp masking still on right now?
Yes,
again?
it is.
We see the difference with it on and off?
Sure, let's do that.
I assume those are going to dim if you turn it off.
Well, the nucleus will dim, okay, and because there's so much density of it, let's do it. Okay, we turn off that, and you can see detail in the nucleus that was previously not visible. And detail is more subtle in the galaxy when you turn that off. But you do need unsharp masking, which is a technique which brings out faint detail that requires a little digital assistance to be seen, and that's what unsharp masking does. So if we turn it back on, you can see how much brighter those got. So
I thought when you had it off, there's a little red area down there, right at the bottom edge of the image.
Let's go see.
It looked almost like it stood out a little better.
Right here?
Yes.
Okay. Well, let's go see. I know I went through. I pointed out many of the areas in the galaxy. Yeah, see, with it on, it actually shows up a little bit brighter, a little more sharply defined. Right?
The blue looks brighter to me, but the red looks dimmer.
Really? So let's turn it off again and take a look.
Can we raise that a little more so we can see it?
That's the extreme bottom already.
Okay.
Yeah, I'd like to. But that's as far down as it goes.
Okay.
We could lower it. I mentioned to everybody. It's like, yeah, it goes off the other end of the image either way, because it's such an extensive galaxy. But okay, we have unsharp masking on. Let's turn it off and see how that looks.
Maybe it's just the contrast between the lower blue now that looks like it popped out a little more.
Okay, and then here it is on.
It looks nicer with it on.
Yeah, it's really pretty though. But you know, that is, see what Daryl's pointing out is this region here. Well, that's kind of like a bigger version of the Orion Nebula in this galaxy. Okay, this is one of those stellar nurseries that we see so many times. The NGC 604 in the Triangulum Galaxy is a massive stellar nursery, and so forth. Yeah, these are really pretty. We have 17 stacked. But you can see this. Here's an example of another stellar nursery. Pretty obvious. Look at that. Here's another stellar nursery right there. That's about the size of an Orion Nebula. Then we have smaller ones that you can see throughout. Like here. There's another one down here. I remember. Oh, I just passed it, I think. Yeah, there it is. Right there. There's a nebula here, stellar nursery. Little one right there. Those are areas of ionized hydrogen. Okay. All right.
That's M32 right there.
You got it. Yep. Here is another nebula, which is really interesting. It has a little glow around it, so it's a fairly compact nebula. And there's a faint one in here, you can see. Yep. We're literally inside the spiral arm structure and dark nebula structure of this galaxy.
That OB association is really nice.
It is. It is. You can see almost individual objects in there. Really pretty. Wow. Alright, well, we did 20 here. This. So let's do two things. Let's turn off the masking for now, so we can catch the whole gradation of the nebula here, or the galaxy. And we'll save this in FITS format, which doesn't affect us in any way. Then I'll save this exactly as seen, turn back on the unsharp masking, and save it exactly as seen again. So you have both versions. There we go.
Sam S. asks, is there an optimum number of stacks?
Yeah, that's a good question. And hi, Sam S. Good to see you. It depends on your seeing and all that, but typically, you'll find people will take upwards of 20 or 25 or 30 stacked images. And I've sometimes taken 30 or 40. I've never done more than that, because then you get like diminishing returns. Sorry, as you want. Sometimes you get diminishing returns after that, but you get to 25 and you pretty much have as noise-free an image as you can get. Now, one way of knocking out noise is by reducing the temperature on the center of the camera. If you look right down here, not there, if you look right here, you can see that it says minus 20 Celsius. That's a target temperature, and that's where I want to take the sensor cooling. And I got down to minus 19.8 right now. So it's literally almost 20 below 0 Celsius in the building. And you want to keep that kind of differential between the ambient temperature. You want to be lower by as many degrees as you can within reason, and that going out to 40 or 50 below 0, again, diminishing returns. But you want to be 25 or so degrees below ambient temperature. So when summertime was around, I didn't have this down to minus 20. I had it down to like minus 10. All right, but I dropped it another 10 degrees when the temperature outside, when the ambient properties were about 14 or 15 Celsius, which is what it is now, 14.
Per the question on stacking,
Yeah.
I know this is a kind of a apples and oranges thing, but just going by what I read, if I remember correctly, when they do imaging of planets, uh, they stack a whole lot more, don't they?
Yeah, because here's how that works. Um, when you take images of planets, what you actually do, in most cases, is you take a video of planets, and you stack the video frames. I've done that. You can use PIP, P-I-P-P, which is Planetary Image Preprocessor, and that'll allow you to do just that. Okay, and when you do that, basically, that allows you to do a huge number of things to each frame, and the more frames you have, the less noise you have. So with PIP, you can routinely be stacking 150 images, because 1 second of video is 24 frames or 30 frames or 60 frames, you know, depending on how many frames per second you have that video set to. And so you take a second of video and you have 60 frames you can stack. And what you typically get is it goes through all the frames, okay, PIP does, and it decides which ones are the best ones, and it rates them. And you can say, okay, only stack the top 50 frames, and don't stack the rest of the 300 frames or 400 frames. And that gives you the best images.
And that's a matter of seeing as much as anything, isn't it?
Yes, it is. You're absolutely right. All right, so this is good. Andromeda Galaxy's up there. Yep. Okay. All right, so now don't we have? There's other galaxies up here we could look at, right? If I recall, we have done this. We don't have any really good galaxies for another half a season up in the north.
Yeah.
Yeah. I think, what's the elevation on this? Let's see what the elevation is. Alright, well, we can try this.
How about the crab? We haven't done it in a while.
I know. I want to look at the crab, but first I want to see if we can check this out. I've been waiting. Yeah, I've been waiting for the crab to get up high enough as well. Let's go to our auto size here for fill the frame mostly with this. Okay. Then come back to our planetarium program. And let's see where the Pleiades is relative to us. And we might still end up facing into the building. It's going to be looking over there, you know. But I haven't looked in a while. There we go. All right. I think we'll be able to do this. As you can see that there's dust around the Pleiades. That's very, very consistent with everything that we've ever seen with the Pleiades. These are hot B-type stars. They're not O stars, but they're B-type stars. So they're not as blue as O stars, but they're blue. Less of a blue hot. Blue is hottest, and red is coolest. So there we go. So this is the Pleiades. And the Pleiades are a hot young cluster. If you wonder why they look familiar, it's because you've seen them on the front of every single Subaru, right? Subaru in Japanese is a word that refers to, in part, unity, and unity is what Subaru's claim is, and so forth. So they use the symbol of the Seven Sisters on the hood ornaments of their cars. Alright, so we'll let this start tracking. And I'm going to show you the nebula. I want to show you how extensive this really is out here.
Pleiades are the daughters of Atlas, the guy who had the weight of the world on his shoulders.
Well, that's because he had 7 daughters, right?
I guess.
All right, we're stable here.
Must feel like you have the weight of the world on your shoulders.
Right.
7 daughters.
Right. Okay, we're off and running. We'll come out of night vision mode here. Go into a live stack here. And we will see it. Hey there, Kevin Burt. How are you? The software I'm using is SharpCap, which is this program here. I'm using Astrophotography Tool, which is this program here. I'm using security cameras over here with software. And then down here is a link. This is my interface to my observatory software that I wrote to control everything going on in the building. Wow. Okay, now the halos are an artifact of the system, very bright stars. I can get rid of those in post-processing. But this is interesting because these bright hot stars, when people say the 7 sisters, that's not all that makes up the Pleiades. A lot of the stars you see in this image are part of this cluster. All right, but you just popularly see the 7 sisters. All right, so let's do a color process here, take care of that. And then let's move this in. Darken up the space around the stars.
There are hundreds of stars in the Pleiades. I think some say there may be as many as 1,000.
Yeah, and what's beautiful about it is that the Pleiades is a cluster of stars that happens to be moving through a dust cloud that we may be part of. Okay, but again, being inside the dust cloud, you can't really see the dust cloud. So that said, when we look at the dust, you have to keep in mind that the dust is going one direction and the stars are going another. That's how they know that the stars and the dust are not associated with each other. They're just passing through, and we just happen to be looking up there at the right time.
Yep. Taurus, there's a lot of molecular dust clouds up there.
Mm-hmm. Actually, in Taurus and in Perseus, there are dark dust clouds that are molecular clouds, as Daryl's pointing out, that we can look at. And you can see these dark dust clouds, and it's just astonishing to see how the convolutions in them. I'm thinking in terms of the Perseus dark cloud. Okay, and then there was a Taurus dark cloud. We might be able to see that tonight. I have to look and see where it is. ZC226 says, really cool to see this all in real time. It is, isn't it? It is just so cool. This is a 35-second exposure, and you get to see it. And the thing that's interesting is I just don't think there's anyone else doing this. This is a live deep sky observatory, man. This is so cool. Izabela says, Mark, how can people see your latest processed images? Okay, I'm working on that, Izabela. I'm working on that. I can show people the latest processed images because I do have them. But they don't need processed images if they don't want them. But if you want to see the latest processed images, actually, how silly of me, go to SkyTourLive.com and go down 2 sections. The first one is the database section. The next one is the photographic print site, and you'll see a gallery. And if you don't want to get a print, that's fine. If you do, you can get it on canvas, you can get it on metal, you can get it as a framed under glass. The canvas is usually the best. Those look beautiful. But you can see the gallery with the processed images there because we do a lot of finished processing work on all those. And we're also setting up a site where you can come in you know, for a nominal fee, kind of like the Patreon thing. And you have access to all of these in digital format, so you can do with them what you wish at full resolution. So that's another thing. So you have access to the fully finished process, the ones where all the halos are removed and everything. And then those are truly beautiful photos. Notice this is amazing. The Merope Nebula is really pretty tonight. This is what this is called. Look at the detail in this. Wow. And this is only 8 stacked. I've not seen it this good, to be honest. I know I keep saying that often. I think a broken record. But look at the detail here. This is gorgeous. Holy cow. Have you ever seen it that pretty, Daryl?
Can't say I have.
Now look at the detail. There's a line here. I mean, I guess that line was there before. The Maya Nebula here, this line is kind of washed out a little bit, but I can fix that. If we do a little processing, maybe I can pull this down. Yeah, see? And now the Maya Nebula shows up right here. Isn't that something? Wow. But you can see the gossamer lines here. And it was you, I think, Daryl, that described this like a brushed, like it was a brushed, combed, I think you said.
Yeah.
Looked like a combed line of dust, which is really pretty.
The Pleiades is one of those objects that the ancients knew.
Mm-hmm.
I mean, it's obvious in the sky when you see it. And they saw it as well or better than we do nowadays. And
yeah,
they took note of it.
Yeah, it's something.
They're probably who named it after the daughters of Atlas.
Yeah,
I suppose.
Again, these round objects here are halos. These vertical, these horizontal lines. There's cables coming out of the camera to the side, because the camera's on the front of the telescope, and those cables will show up. And that's common with this type of setup. But the benefit is you get to see 4 full moons across and 3 full moons tall of field. We see the entire Pleiades in one view. Let's just back out. That's the size of our field right there. Isn't that pretty? Thank you, Claudio, for the compliment. That's nice. And same with you, Michael. Thank you. And Bonnie. Cosmic Ray says, is the dust at the same distance as the stars? Approximately, because the dust is scattering the light from the stars. So the stars are mingling with the dust. But some of the dust is farther than the stars are from us, and some of the dust is closer. Some of the dust is at the same distance. So that's sort of like a non-uniform dust cloud that they're traveling through. And that dust cloud, as I mentioned before, might be very extensive, moving many light years, being many light years in size. And we may also be in a dust cloud like this, if not part of this same dust cloud. We just don't know it. There's some research to indicate that we are in a dust cloud.
When we see the Pleiades, they're about 400 light years away. And when you look up in the sky at Taurus, you see the Hyades, the head of the bull, that V-shaped cluster of stars. It's about 170 light years away. So, and then when you see Aldebaran, the eye of the bull, the red star, it's about 70 light years away. So when you look up at the head of the bull, you can kind of get a 3D feeling for what you're looking at. 70 and 170 and 400. You get sort of a sense of depth of the sky in that direction.
Yeah. You know, what Daryl says is very important to understand. You know, it's a 3D universe, and you can't forget that. You know, when you look at stars that are nearby, Okay, some stars are a cluster of stars, but you don't even know they are. Okay, one such cluster of stars is the Big Dipper. That's a cluster, and they used to think that we were part of that cluster of stars, but we're not. It's actually moving in one direction, we're moving in another.
First major moving association.
Yep, and so of those stars, you know, because we're in and we see this Big Dipper in the sky, you don't really think about the fact that that's a star cluster. You used to have a star cluster being like this, or like this, you know, the Pleiades, or a globular cluster, or a cluster of stars like we see often, that we show a little cluster of stars that fills up the screen a little bit. But that's not always the case, right? If you're within it and the stars are separated a little bit, you might not even know you're in a cluster. So again, it's a 3D universe, and the closer you are to these things, the bigger and more extensive they are in your sky.
Cosmic ray, I wouldn't think they wouldn't eat up the dust. They could certainly be blowing the dust away from them. And to a degree, you might be seeing that now. I never can tell which one is which, but the star to the upper left of Merope.
That's Alcyone.
Alcyone. That looks sort of like the dust is billowing away from it. It's just
it looks it. Like. It looks it, but don't know for sure.
Yeah.
Don't know for sure.
Mean, this is the difference, though, between when we look at the Eagle Nebula or similar things where the stars are forming inside the dust and they're tending to blow the dust away and destroy the trunks or the columns, whatever you want to call them. And this where, you know, they're just passing through. And they may not be around long enough to really cause much damage to the dust clouds.
Yeah, and keep in mind that the dust clouds are made of more than just atom-sized, objects. Okay, they're made up of aggregations of lots and lots and lots of atoms to make true particles that are in the micron range in size. And so, those particles are capable of withstanding the radiation coming from these stars. But they scatter the blue light coming from the stars, which is why you see it as blue. Again, the same reason our sky is blue is why this nebula looks blue. It's not that it's the color of the stars that they're reflecting, it's that they scatter the blue light. If the stars were orange, you could still get a reflection nebula. It just won't be as intense because there wouldn't be as much blue light in the spectrum of the orange star. A white star, sure, you'd see blue nebula. Okay, in fact, we do. We see that. So it's a matter of the fact that these particles of dust, because of their size, their composition, they tend to scatter the high frequency light easier. And by scattering, we mean absorb and re-emit in any old direction. Okay, so that's what they do, and that's why in all directions the Pleiades will have a blue nebula around it, seen from any which angle. Okay, so that's really how that stuff works. So the only interaction, cosmic ray says, so the dust doesn't interact at all with the stars. Well, the only interaction is the scattering process. Now, it's also possible that as the dust gets near the star, maybe the gravity of the star could create some type of disturbance in the direction that that the dust is moving. That almost certainly is happening. So you might see in fast motion, as the Pleiades passes through, you might see like a turbulent swirl formed because of the passing of the star, or all the stars in the Pleiades collection through this dust. They don't leave it unfazed. They will affect it because the mutual gravity can tug and pull on the dust particles for sure, and it'll drag them out into new shapes and so forth. Maybe the way this combed look is that we talk about with this is precisely because the cluster is moving in that particular direction. I don't know. I'm not sure which direction the Pleiades are moving as we see them here. I have to look that up. I'm not privy to all the research being done everywhere. I know some, but not all of it. Hello, Prow. So, but that's just, you know, for the record. If anyone has any other questions, please feel free to ask. And check something here.
Can we zoom in on that a little bit?
Yes, we can. Which section would you like to zoom in on? The Maya Nebula? The Merope Nebula?
You can keep the whole thing in view if you want, just to
Okay.
get a little closer to it. Well, I always wondered, I mean, when you look at that, the star on the far right, you see what looks like two almost parallel horizontal streaks, and just the different shapes and curves and whirls of the clouds
Yes.
around the different stars. Yes, that, and then over at I think you said it was Alcyone.
Yeah, you got this billowing.
Yeah, that the the ins and outs and the curves and the whirls of the gas and all is quite different from star to star.
Yeah.
That the stars could be affecting the dust somewhat.
Yeah, I mean, certainly they do. Now, as far as pushing the dust around, it's possible they can push the dust around. These are B stars. Alcyone has multiple components, I think, and thus would stand a better chance of moving the dust around. So maybe this billow is a short-term effect of the stellar winds from that star pushing out that material. Not sure, but it'd be interesting to see. If this, for instance, if this dust here is moving on a radial path away from the exact location of this star's combined center of mass, then we could say with some authority that that dust billow could very well be due to the stellar winds created by Alcyone.
Do you remember the story behind the lost Pleiad? I mean, they call it the Seven Sisters, but
Yeah.
most people, when you see it up in the sky, they only see six.
Yeah.
And, if the Greeks or whoever named them the Seven Sisters, there's some thought that, what happened to the seven sisters.
Well, I mean, we have 1, 2, 3, 4, 5, 6, 7, 8. I mean, so which one? What is the seventh? Is it this one or is it that one? Probably this one. I don't know the story on the Lost Pleiad. Hey there, JSCO. Good to see you, man.
Let me look.
Meanwhile, I'll answer Mike Hedrick's question. Are we able to see the dust move, say, over 30 years? Well, we've been taking pictures of the dust clouds for a good part of a century or more. And I don't know that they've noticed anything moving. It might not be enough time.
Well, there's a poem about it, and there's a work of art about it.
About the Lost Pleiad?
Yeah, there's a sculpture, the Lost Pleiad, made by Randolph Rogers, about 1875 to 1881. The Lost Pleiad personifies one of seven sister stars, described by the Roman poet Ovid in his poem Fasti. Her brightness dimmed by the shame of marrying a mortal, the Pleiad anxiously searches through the night sky to be reunited with her sisters. I'll post this in chat in a second. It's a neat picture and story.
Okay.
But anyway, so yeah, evidently there is like a myth behind it, I guess.
Mm-hmm.
Cool picture too.
Okay, cool. Okay. So I saved this now. So that's been saved. The dust is exceptionally beautiful right now. I mean, it's really showing up very nicely. Very pretty.
Posted the link in chat. She's looking for her sisters.
Okay. Alright, so we can clear this now and move on to the next item. Let's get back into night vision mode here.
I learned something today.
About the lost Pleiad?
Yeah.
Cool.
She married a mortal and forfeited her position amongst her 6 sister stars.
Wow. Okay.
And here's another one at the Brooklyn Museum. Must be a different artist. Nope, that's Randolph Rogers too. Maybe it is the same one. Anyway.
Alright, so let's go here. I'm not sure we can see this. But it looks like it's not going to be visible to see the Crab Nebula yet, but we'll try it. I think it's going to be behind the building. Yeah, see, it's going down behind the building. You can start to see the red light of the telescope LED. There's the crab right there. So, and too many distortions. You can see the distorted stars.
I can see in your telescope view this looks pointing right out the roof.
What's that?
I'm sorry. I see in your telescope view it looks like the scope is pointing right at the edge of the roof.
Yeah, so that's not going to produce anything good for us. And that means that the flaming star, which is not the flame nebula, but that's, again, not good enough. We don't want to look at that. Oh, but wait a minute. Well, this is always fun to look at. Let's go here anyway. This is beautiful.
Double cluster.
Yep. Yeah, this is just one of them at the moment. I've got to move it over to show you the rest. Let's move west. And the other one comes right in. There we go. Double cluster is probably one of the most beautiful objects in the night sky. It consists of 2 clusters at different distances from us by a couple hundred light years each. And you know, I think the one on the left is closer to us. This one's farther away, so they're kind of like this in the sky. But because they look close to each other, you know, you see them right next to each other. They look like they're right near each other because we tend to see flat projections in 2D. But that's not the case. And we'll just do some 25-second shots of this. We're guiding now. We should be able to just do a quick stack of, say, 5 or 10 of these just for the time being. Meanwhile, we'll look for another object to go check out. we have the Heart Nebula and the Soul, which we looked at the other night. Well, we did look at the Great Lacerda Nebula. Remember that?
Yeah, it was very faint.
Yeah.
And it turned out we're only seeing a small part of it. It's quite large in the sky.
Yeah, so let's find... I think the Spaghetti Nebula, that's may not be up yet for us. It might be off in... Auriga? Let's go see. Let's just see where that is. I don't know its official name. Oh, it's right there. Look at that. It's named the Spaghetti Nebula. Yeah, it's not ready for us yet. It's in Auriga. It's, well, it looks like it's close to Auriga. What constellation is that actually in? Taurus. It's in Taurus. So we're not quite there yet. The Spaghetti Nebula is really pretty. It's this very, very large object. It's near Mars anyway. Alright, well we'll keep that on the back burner and see if we can look at it. Let's look at this on the other hand. Wow. Talk about too much stuff. Alright, so let's bring it down. Color correct this. Boom, look at that. Now, you've heard us mention before, there's these beautiful red stars in here. These red stars are, I guess we discovered yesterday they were red supergiants, weren't they?
Yes.
Yeah. Interesting, but they're not part of the cluster. Because they weren't formed when the cluster was formed. They're much older than the cluster. Because when you have a supergiant red star, it means it's gone up what's called the asymptotic giant branch, meaning they're no longer fusing hydrogen into helium. They've gone way past that. They've used up their hydrogen. Now they're burning shells of helium into carbon and shells of carbon into nitrogen, and they're actually they've evolved off of that fusion of hydrogen to helium line that we call the main sequence on our star chart, on our Hertzsprung-Russell diagram. And so those stars are highly evolved and heading toward extinction. And that extinction can be in the form of a supernova. That extinction can be in the form of a supernova that leaves a pulsar, leaves a neutron star, leaves a black hole, depends on the mass. So that's pretty cool. Oh yeah. What a beautiful object this is. Very, very pretty.
This is a good binocular target, Hedrick.
Yes, it is. In binoculars, it might look. You might see it more like this. It's just beautiful. They're a very rich pair of clusters. Hey Kevin Burt, I actually mentioned earlier. I mentioned this is Sharp Cap. This is astrophotography tool. This is our security cameras. And this is access to a microcontroller program I wrote to control the various object or items in the observatory.
Your camera controls, those are part of Sharp Cap too, aren't they?
Yes, this is Sharp Cap, yep. Yep. Telescope controls are astrophotography tool. Camera controls are Sharp Cap. Yep. Louis Toss says, are those supergiants big enough to cause a gamma ray burst? I don't know the masses, but if they're big enough to go supernova, then you may get a burst of gamma rays. Before any supernova, what you will get first is a bunch of neutrinos. And if you see a stream of neutrinos coming from a certain point in space, you can be sure that the supernova is right on its heels. Because that's the very last thing you see before the star goes boom, is the neutrino burst.
Big bada boom.
Yeah. But neutrinos are not gamma rays. Neutrinos are other particles released. They go right through the Earth as if it's not there. They can be captured in deep mine tanks of special water capture tanks. And that's how we know they're there. They were theoretical and then discovered through that way. Oh, and Kevin Burt, sorry, the last one is this. This is Stellarium. It's free. You can buy, or get Stellarium rather, for free. And we use it with telescope control, which is kind of built in. It's kind of kludgy with Stellarium, but it works. And we have other ways of getting the things. We have a full database within this guy, a full database within this guy, and a full database within this guy. So we can, and we have 3 different databases to look with for objects.
Wow, you have Stellarium up right there.
Yeah.
Can you freeze it right about there? I'm sorry.
Wait, what do you want to do?
Well, I'm going to talk about Mars for a second.
Oh, okay.
You see Mars there. It is between the tips of the horns of the bull, Taurus. And I have mentioned before that Mars was moving west to east in direct motion, and now as Earth is catching up with Mars prior to opposition next month, less than a month from now, could you back out till you can see the horns of the bull again? That Mars recently started moving retrograde in space again, to where it is moving west, or it is moving east to west now. It was down to the lower left of where it is now. It was just outside the tips of the horns of the bull, and now it has moved backwards, back in between the tips of the horns of the bull.
Which are these right here?
Yes. And that is the sign that Earth is about to pass Mars as we both orbit the sun.
Mm-hmm.
That it makes Mars look like it's moving backwards in the sky. And Mars is up by 6:30 at night now. I went out and saw it tonight when I went out and checked the mail.
Yeah.
So it's up earlier every night.
Yep.
And when it's at opposition on December 7th and 8th, it'll rise at sunset.
Yep.
And by then, well, golly, sunset's going to be about 4:30, I think.
Mm-hmm.
Okay, thank you.
Sure. Right, and now from this position, we will save this. All right. This is more than enough. I mean, we've got like 20 stacked right here. So we'll save this just like this. We'll save the data, and we'll save the exactly as seen imagery. And then we're going to go to one of those molecular clouds I was telling you about that are just so cool to look at.
Izabela asked an interesting question.
Okay.
Are there, and is it even possible to have clusters of supergiants? Of red supergiants, because they're old, clusters, open clusters of stars tend to come apart over time, and they're more likely with younger, like blue giant stars.
Yeah. Hasn't been enough time for them.
Like the double cluster, and there hadn't been enough time for them to separate yet.
Right.
By the time you get to red supergiants, they're probably much older, and they're less likely to be in clusters.
And they're already independently moving on their own, so that's something that makes a red supergiant cluster something that will be very rare.
Yeah.
Okay, we're going to the Perseus cloud here. Just inside Perseus. It's called the Per cloud, and we should be able to see it because, and this is actually a very interesting cloud. We can already start to see it a little bit here. We're gonna come back to our 33%. All right, so you can see a little bit of a nebula here, but you'll notice that the stars seem to be blocked by something here. That's pretty interesting, and you can start to see some detail in here. There's some really intricate nebula in here that I'm about to show you. Okay, there it's right here. All right, so let's wait for us to get our guide star. I can't wait because this is a beautiful object. And we'll do a 35-second shot on this. I was going to go to 40 or 50, but I'll do 35 seconds. All right, we're guiding, and I think we're stable. Yes, we're stable. Here we go. This object I took a picture of only one time, and the one time I took a picture of it, it was really beautiful, and it was so gossamer that it was unbelievable, and I just couldn't stop staring at it. Hey, good night, Cyclone. Thanks for coming. Off to bed. Don't give your mom any trouble, Cyclone. Okay, here comes the first one. Okay, we see this here. And we'll see more here shortly. Okay.
I'm not sure I remember this.
Yeah, I'm wondering if I should go to the right a little more. I think I need to, but there's stuff up here I want to show too.
What is this called again?
It's the Perseus cloud, molecular cloud. It's right here. You can see it's blocking the stars behind.
Yes, I see.
Which is really cool. I do want to actually, I'm going to do that. I'm going to clear it and I'm going to move it over. Because I do want to catch it better. I want to actually show it a little better. So let's do 1 second again. Okay, that star I just want to move over. So we're going to move that over. Which I can do. Okay. And do this. Okay. Now we'll find it again and go through it again. This will be the Perseus cloud.
Cindy, that's the Horsehead and the Flame Nebula. That's funny how that opened inside the chat window with what looked like a smoke drain from a meteor flying in front of it.
Is that the link she put in?
Yeah, I never seen it do that before. It opened right in the chat window.
That's why I can't open those there, because it does. It opens up in the chat window. And so I don't open up messages in the chat window directly. I'll copy them and open them in a browser.
Huh.
She retracted it though. You didn't have to do that, Cindy.
I'd never seen that before.
Okay, we're gonna do 40 seconds on this guy. Off we go. We're guiding. Yeah, I think it's a little better. Okay, live stack. And there we go. Okay.
Izabela, if I understand your question, It is the Perseus cloud.
It's a molecular cloud in Perseus. Yeah, it's abbreviated the Per cloud, PER. Oh, there we go. See, it's over there. Shoot. All right. I'm going to clear it again. I want to make sure we get this thing. This is beautiful. All right. Okay, so let's move it over. Oops. I might have gone too far.
Excuse me again just a moment, please.
Alrighty.
Right back.
Okay. Yeah, I think that's it right there. Okay, so I'm going to move over a little more. Okay. This is a beautiful cloud. I'm going to take a 45-second shot, just a little finder shot before we even get our guiding going. Oh, Cindy, you didn't do anything wrong. You're able to put links in there. Cosmic Ray talking about the Perseus molecular cloud. Alright, let's see how this looks. 10 seconds. Get your stuff together. 5 seconds. 2, 1, 0. Zulu time. Yeah, that'll be it. Okay. Now we'll do a live stack. And we will clear it. There we go. We can't put the whole thing in here, array, because it's much bigger than our field of view. We're 2 degrees by 1.5, and this thing is like 7 degrees in size, roughly 5, 6, 7. Okay, here we go. Here we go. All right, this is nice. This will show it well. All right, let's do this. There it is. The Perseus molecular cloud. There's a reflection nebula here. Interesting, Cindy. If you could put that link back in, I'd like to copy it and move it to a browser, okay? Because when you retract the link, I don't know exactly what it was you were talking about anymore, which I'd like to know. Let's color correct and make the color a little more normal so that we can see the background better, the stuff we're looking at. There we go. Okay. Alright, so let's now drop down a little bit. Perseus cloud, molecular cloud. It's right here. Part of it, anyway. It's much more extensive than what I'm showing you. Welcome back, Daryl.
Thank you. That's cool.
Yeah, this is the Perseus cloud. We got some interesting details in here. We have to just let them flesh out a little more. You can see how this part of the cloud is related to this part of the cloud. There's a reflection nebula here.
Mm-hmm.
Alright, so now let's move this over a little. Start to show the details. The Perseus cloud is many degrees in size beyond what we have. It's like 3 times the size of our image. And that's okay. Alright. Alright. I'm gonna go get I have to get something to drink. I'll be right back. We're just integrating on this object right now, and I shall return momentarily.
Okie dokie. RRAWWBB is the reddish haze emission nebula. That's a good question. We may be kind of treading a fine line here. Sometimes when we see dark nebulosity, it can assume sort of a brown cast if there is illumination in the area. It's not really emission nebulosity. It's just the dust is catching enough light to show it as like a brown cloud instead of a black cloud. And that's different than reflection nebulosity, which is blue. As Marc says, it's which case it's Rayleigh scattering. In this case, I'm not sure. Good question. Maybe we could answer that when Marc comes back. Hello, Jessica. C. Ramos, how does astrology get the info from the stars?
All right.
That's a loaded question. That's people casting human characteristics into the sky.
Looking pretty.
Long time ago, astrologers and astronomers were the same thing, but we parted ways a long time ago.
Oh, hello there, Raw WB and Jessica Thinks Creative. I like that. Welcome to SkyTour Livestream. Please subscribe and like us and hang with us, because we do something very unique, I think, that not many people get a chance to see. So do give us a thumbs up, and do
Marc,
hang with us. Yeah.
Our WWBB asked a question: is the reddish haze emission nebulosity?
If it's a molecular cloud, most likely it's supposed to be brown, and maybe the color's a little off. Because you're talking about this haze.
I assume so, yes.
Yeah. Let me see if I can color correct that and see if it changes the color.
I don't know if I gave him a good answer or not.
Yeah, see, color correction shows that it's more of a brownish hue. I think this is part of the molecular cloud.
Okay. So it's
we'd have to look that up though to make sure, because Just going by visual, it can be fooled. But this is really pretty looking.
Yeah. I said, you know, I didn't know if it was red emission nebulosity or brown, slightly illuminated dust clouds.
Yeah, I would say that you're right on that latter part, that it's probably slightly illuminated dust clouds from nearby stars. Perhaps this one, maybe these guys actually. This might be a foreground star for all we know. Proficient asks a question: if the James Webb was pointed towards Earth, would we see the past? And if so, how far back would you guess? The James Webb's 1 million miles away. So if it looks back, it's going to see us basically a fraction of time before. Like if you say the instant time, like here, okay, 93 million miles takes 8 minutes. So 1 million miles, okay, you do the math and figure out the fraction of time it takes for light to get here. That's the amount of time it would actually be delayed. So when it looks back at the Earth, it does see it slightly behind real time.
Roughly 5 seconds.
Yeah, so it's about just like what 1 million miles would do. You know.
Yeah, a little over 5 seconds.
So it'd be looking back in time about 5 seconds effectively. Okay, let's see if I can tease any more data out of this.
That is cool looking, Mark.
Yeah, it's a nice cloud. And
See.
let me use this. This will help us see more of what's in there. Yeah, look at that. See, now you can see there's more in here. And there's actually more down here.
Mm-hmm.
Yeah. Very pretty.
It is.
Let's see if...
I don't think I have seen that before.
No, I don't think so. I mean, I imaged the Perseus cloud a couple years ago, but not recently. So let me try something else. I want to try and darken up the space in the background. And so as long as you don't come too close. How's that look? Let's see.
That's nice right there.
Yeah, that's looking pretty nice.
You see hints of the really dark stuff in the lower right quadrant, and
Yeah.
really stands out there in that upper right part.
That looks good. That looks good. Yep.
That's cool.
So when we say molecular cloud, what do we mean? Okay, I talked about the dark dust made of carbon atoms and silicate atoms, and there are actually molecules of carbon, molecules of silicon, but there's other molecules out there too. There's a lot of ices. This is the cold depths of space. This is the cold darkness from whence stars and planets are born. That's where they come from. So this dark nebula in space, this is where it's at. That is, for me, the most important, fundamentally, the most important places in the universe are hiding in the dark. The dark cold of space is where it all happens. Yeah.
That's where the boogeyman is.
That's correct. Yeah. C&D Boy says, once in a lifetime view every image. Except that we'll image it more than once, C&D Boy. So it won't be once in a lifetime. You know. But this is just pretty, and you know, there's so much science going on in this cloud. You know. So the molecules of dust and so forth that are in here, molecules of gas, you have diatomic hydrogen in here as well. And all of that is gravitationally condensing perhaps in here. Now, you asked the question earlier, I think it was Proficient, about the James Webb. Well, if you point the James Webb at this, and you look in here where we can't see what's going on in there, the James Webb could probably see how many stars are actually in their prototypical stage, in the protostar stage, where they're not quite winked on yet, not doing hydrogen fusion, but are underway possibly toward that goal. That's what the James Webb has been good at, and showing that there's way more stars than we ever thought there were. Let's see if we can... Yeah, that looks good. Okay. Take us up and... No, it's just a tiny bit. Oh, that's looking... See, now you actually see... Because we've stacked 17. Alright. And doing so, you can actually see how... Almost you can see a three-dimensionality here. It looks more like it's solid.
Yeah.
And that's important, because that shows we're actually getting a lot of depth. Means that we're getting a lot of data that's useful. Let me try just softening that noise just a little bit. How about that? Wow. There we go. And for now, what I'll do is I'll just remove this guy so we can watch it grow. And let's get rid of this. Go full screen. And bring this down. Ah, look at this. Now, this is what astronomy should be, guys, don't you think? Just pointing a telescope at a nondescript spot in space and seeing something there that you've never seen before. You know, and then you get to hear about it. You learn about what these objects are, and the significance of them. You would not be here if not for places like this in space, because you were born of one of these types of molecular clouds. The sun was, and so were our planets. So that's a very important development. And that's why I say often that, to me, okay, when I look at something like this, to me, this is my cathedral. The universe is just, without question, one of the most beautiful things that I have ever witnessed in my life. And another thing is, I'll be long gone, and this cloud will still be there, just like this. For other people to see. Donald Kunzer says, is there a name for this object up here? There might be. Let me go see if we can find that for you, Donald. Okay, because I do know... where's the per cloud? Let's go. Okay, that's the per cloud. Okay, the Perseus cloud. It might be IC348. It might be Vandenberg 19. It might be Lindsbright Nebula 758. It might also be Gingrich 1. So that's where this is. The Perseus cloud is defined as being all of this. Oh wow, look at this now. It's sort of taking on a whole new life. You know? That's nice. Wow, I like that. Cindy put the link back in? I think she did.
Yeah.
Okay, I got it here. Oh, why can't I copy it?
I can try to drop it in chat, in your chat if you want.
Oh, hold on. Let's see if I can do it. Interesting. Yeah, if you could try and drop that. I can't copy it for some reason. Thank you, dear.
Sure. Thank you, Sandy.
Did I miss something?
No, I was just thanking her for posting that link again.
Oh, okay. Oh, I thought you said Sandy. You said Cindy.
Cindy.
Oh, okay. Right.
Cindy.
Interesting.
This reminds me of last year we just took off down in the southern sky and started trolling our way up
Remember that?
the dark rift in the Milky Way up towards Cygnus.
Oh yeah.
Started finding all sorts of random dark nebula and stuff.
Yeah. I think that was before we actually had the ability to do plate solving and figure out exactly where we were, was it?
It was. That's correct.
So we were just trolling because that's all we could do.
Yep.
Hoping we'd find something we recognize, but now we don't care about that because we can point the telescope anywhere in the sky and it can tell us where it's looking just with a short little, plate solve where it looks at the pattern of stars and figures out where we are.
I don't remember the details. We had something... you might have been having a software conflict at the time between the Stellarium and the other system, APT or whatever it was,
Yeah.
and we were kind of flying blind for a while there.
We were, yeah.
Just went wandering and found all sorts of cool dark nebulas along the edge of the dark rift in the Milky Way.
Yeah.
In the summer sky.
We did indeed. So that's really what's there. There's a lot going on in there. Look at that. These diagonal lines I'm going to get rid of because I'm actually thinking of changing cameras. So, still working on that. Alright, so if we bring this down to here. Okay, that's the cloud without any processing to it. And then this will give us processing a little bit. Alright, and then this will give us processing a lot of bit. There we go.
So you look at that now, and boy, you could almost say that looks like faint emission nebulosity.
Yeah, I have to look this up and see if there is a faint emission nebula associated with it. Again, the color correction you have to be careful with, and I'm not sure I got it correct yet. Boy, it's pretty.
It is.
Jessica thinks creative. Bye, beautiful peoples. We gotta get the syllabus for today organized. It's such an awesome stream. You've such an awesome stream. Thank you for your hospitality. Oh, of course. Jessica, you're always welcome back. Make sure you subscribe and thus hang out with us when you can. We will always welcome you. Good night. Did Izabela go too?
No, I think she said she was going to go to bed as soon as the stream is over.
Oh. All right.
I am too.
Yeah, this will be one of our last objects, if not the last object I know that we have.
I had a rough night last night.
Did you?
Yeah.
Yeah.
I might have slept about 4 hours, and then I wound up taking a long nap this afternoon, which was a mistake.
Uh-oh.
I was really out of it when I got back up.
Okay. Okay, we've got 30 stacked. We're going to go to 31 here. That's it, 31. And we will save the Perseus cloud stack, and then we will...
I'd like to see it if you do post-processing on it.
Oh yeah, I will. And save it exactly as seen.
That's really cool.
Yeah. And now, for our last object of the night, we're going to go to another object which I think many people find fascinating. Alright, we'll go in our mode here. We'll go in our night vision mode. And let's bring back our telescope. Okay, there it is. And let's go and find this object here. Right there.
California Nebula?
You had to give it away. It's pretty obvious, right?
Yeah.
Yeah. And this one is big. Look at this. You can see this taking up lots and lots of our space, man. This is an emission nebula. It's a softly glowing emission nebula that is in the constellation of Perseus, I think.
It is.
And I will be centering it up, moving a little bit to the west, and then taking the telescope slightly north to do the best to fill in the frame with as much of the California Nebula as we can. Hard to believe that this is an object that's just sitting out there to see. It's really such a stunning object. Let's move over one more blob here. There we go.
And that bright star in the lower right corner is what's illuminating it.
Right. This bright star is putting out a lot of stellar winds. And you'll notice when we take the picture that this front is curved. And that curve tends to match the distance from the star. It looks like the star is basically pushing this material, which is what happens. You know, it ionizes the material, ionizes the hydrogen, making it glow red. And then it kind of pushes the material along with its copious stellar winds. So let's check it out, shall we? This will be a 30-second shot.
And that star is Psi Persei, Xi Persei, XI.
I believe it is. Let's go here and look. It's Menkib.
Yes, Menkib.
Yep. And that's is that Xi or Zeta? I'm trying to remember. Oh, that's Xi. Okay. Yeah.
Menkib.
Menkib. Yep. Well, there it is. and we got a good showing, so now we'll stack that. What's the beauty of this stunning nebula? This is a beautiful example of how stars sculpt nebulae. Okay, when the Rosette Nebula comes up, you can see how clusters sculpt entire nebulae as well, because it's nowhere else but in the Rosette does it show as blatantly. But here is an example of how Menkib is sculpting this place as well. Let me just give us a quick adjustment. And look at that. Remember that curve I said? Here's Menkib. It's a bright, hot, young star. And look. See that curve? See this curve? Okay. Clearly Menkib is sculpting some of this nebulous gas. It's pushing it away. And perhaps there was more around it in the earlier years. Okay. Now the star Menkib is right here, and Menkib is it's an O giant star. Okay, it's an O7.5 giant star. Those are the hottest and bluest in the universe. So this star is only going to last a few million years, and then it's going to go into a supernova and explode as a supernova. It's already on that path.
Can you open Stellarium again for a moment?
Yes.
Just a sec. Can you back out a little bit? That's not far from the Pleiades, is it?
No, Pleiades right here.
Yeah, that's what I was thinking.
Yep.
Just a little bit to the
south.
North? South?
Yep. Yep.
Okay.
Yeah, and then you keep going. And
South?
Yes.
North?
No, south. It's to the it's to the north. Yes, Pleiades are to the south. Okay, because you follow the equatorial lines. And
right.
Yeah. See. So then you go a little bit more, and you go to the double cluster.
Mm-hmm.
You know, so it's sort of along that line.
Thank you.
Sure. Okay, so now we'll come back to this. Okay. So there's Menkib, and there is the California Nebula. So named because it looks like California.
I wish they all could be California nebulas.
That's right. California blobs. Wow. Now what's interesting is in this nebula, it's mostly gas, and there's some dark nebula in here, like this here, there's some here. But that little tiny dark nebula is sort of isolated in here. You know, I've looked at this, and to me, it looks like an abstract image of an elephant. Here's the eye, here's the forehead, here's the ear, here's the trunk. Which might
like
be
a fire-breathing dragon to me.
Well, I guess that's also true. I can see that too.
Thank you, Izabela.
Yeah, thank you for putting that up there, Izabela. Well, I hope you guys can see why I love astronomy. Man, we got so much to see out there, and there's so many things to talk about. It's amazing. So yeah, so this California Nebula, right now, in terms of where it is in the sky, it's in the constellation of Perseus. Perseus, of course, is this guy right here. He's holding Medusa's head, and he's right near Andromeda. and Auriga. And so within Perseus, we have this beautiful nebula. And let's yeah, here it is. So in terms of the distance to this guy, we're talking well, it says here about 1,300 light years. I'm not trusting of much of what this program tells us. But interesting you called it a dragon too, because this actually is the other name, the Dragon Nebula.
Huh. Now, if you see that lower left part coming up, where it gets bright, that's like the dragon's mouth and his nose.
Okay.
And then that lower left part is like the flame coming out of his mouth.
Gotcha.
The head of the dragon is going on up to the upper right.
Yeah.
And maybe that dark spot is the dragon's eye.
Huh. Hello, David Schmidt. Welcome. Good morning to you. David Schmidt's over in Thailand. I dare say, David, you're probably our most distant patron.
You're far out, man.
Well, until someone comes in from a moon base or on Mars, you know, you're it, man. You hold that title.
He's only halfway around the world.
Well, if he's all the way around the world, then he's not far at all, is he?
Right.
Far out and in the future. All right. David, I didn't know you got a puppy. What'd you get, man? What kind of puppy? Is it a Bangkok street dog? Isn't that pretty, David? It is. It's beautiful, beautiful, beautiful California nebula. Let's write this. This is also known as the diffuse nebula. So that's what that is. California nebula, otherwise known as the diffuse nebula. Gorgeous. Let's see if we can increase some contrast here. The answer is yes. Look at that. Wow. Let's maximize this for now. Why not?
Oh,
right?
God, he got a husky.
You did?
Yeah.
Oh, did you be able to look in this?
I'll put the link in your chat.
Okay, how come I can't see links? Oh, I see what I could do. Alright, did you put the link in? Here it comes.
I did.
Alright.
I see a cat and a dog. I assume you're talking about the dog. I would think a husky would burn up in Thailand.
Is that a husky or a Melamed?
Well, it's like a husky to me. A Melamed is just bigger cousin to a husky.
Yeah.
I think Malamute's more mellow though.
Wow. What a cute doggy. I'm guessing the brown one in your lap was the new one. He has like a Tycho, like Bill, New York Skywatcher.
Very much. Maybe that's why he calls him Tycho, or Psycho, rhymes with Tycho.
That's cute. I just want to say one thing, guys. You know, for those that are new here, everything you're seeing here is live. You know, you're seeing this live. This isn't taken before and shown now. You're seeing it come out live. And there's literally nobody doing this. David Smith has a question about the cameras. Could you set the camera to take short vids instead of single shots every few seconds? If you use the cloud memory, couldn't that wouldn't be a problem, right? Yes, you can take short videos. That's right. But what do you do with those videos? You could actually take them and use the individual frames to stack images. People do that with lunar and planetary images. We talked about that before you came in, David. Actually, tonight. And but taking individual photos is just better, because when you take videos, you don't have the option to stack them and end up seeing it like this. You see the original image, and it's much more dull. You can't see what's going on in there unless you stack. So
David, trying to image for meteors through the telescope would not be a good idea. It has a small field of view, and you want a large field of view when you're looking for meteors.
as wide a field as we do have, which is 2 degrees by 1.5 degrees, that's not a lot in a night sky, and the likelihood of a meteor coming through the field is rare.
Yeah.
Although Cindy just showed us an image of the Horsehead and Flame Nebula where a meteor did come through the field, apparently. Is that what that was?
Yes.
Wow.
It was the smoke train from a meteor.
It was beautiful. Okay, now this is 25 stacked. And we are done with this. So we'll pause it. I will rename it California Nebula. So will LiveStack go up and save this? And then we'll save exactly as seen. And there we go. How nice. Alright. Now, okay. Alright, so now what we do is we kill the stack. Come in, do our 1 second shot. This is going to be our... There it is. So, here's our night vision shot. Alright. And looks pretty good. Interesting how this looks. Alright. Now, I think I said this was our last object, right?
Mm-hmm.
Yeah. But I always do one more, don't I?
Yep.
So we're going to do the Northern Trifid Nebula. And it's just a encore. Northern Trifid looks like the Trifid Nebula, but smaller. There it is. David Schmidt says, I thought it might be easier to check for meteors when reviewing single shots. Well, okay. Yes, that's true. And that's why I use the all-sky camera. And I did use the all-sky camera last night as well. And so all night long we took 12-second photos, David. And I have to build those into a video tomorrow so we can actually see if there's any meteors on any of those frames. That's a good use for the video approach. But there are individual photos that are linked together to make a logical video. Okay, let's bring back the telescope here for a sec. All right, come on, where'd you go? Move over. Come back. That's better. Okay. And then let's move this over. And this is no longer the California Nebula, so we'll pull that out of there. I've actually never deep imaged the northern Trifid Nebula. There's a lot going on in here. And this is our encore object for tonight. All right. So we'll let our search begin. If we zoom in, you can see sort of what it looks like. It has lanes of dark material in here. Okay. We're imaging and we're stable. We'll do a 35-second shot. It's off and running. And our live stack is going to town. I'm really excited to see this. I haven't seen this with this kind of depth of exposure before. My neck's hurting from axe throwing yesterday. First time I did it. Alright, let's see what we got. Oh, look at that. Wow.
Looks like a little Trifid.
Yeah.
Sorry, I'm sneezing my foot off.
That's okay.
Well, I did not hear about the bright meteor in southern Ontario. I was in Hamilton, Ontario once, a long time ago.
Hey, I was in Hamilton.
Sonic boom.
Yeah. Okay. Let's see what else we got in here. All right.
Did you just send me something?
I put the link that David stuck in there. I put that in there just to have it, to see what it was that he was putting in.
New York Times?
And a meteor story.
Oh, let me see. Oh yeah, that's it. Fireball flashes above Ontario, parts of the U.S. Whoa, nice.
What?
Oh, they had a video. Looked like it was flying right by the CN Tower or something. Nice video. Yeah. Very nice.
it looks really pretty, leaving a trail of sparks behind it. Burn products. Cool. Well, this is so you guys have an idea what we do on a regular night basis. As Orion comes up, it's just woof. There's so many objects to choose from. Our streams can get pretty long. And if you know objects you'd like to see, you can recommend them. And we read our chats and we interact, and we'll bring you in at times if you want. Oh yeah, look at the northern Trifid. Looks really interesting here. It's got more detail than I remember seeing before. Wow.
It really does look like the Trifid.
Look at this. That's pretty cool.
A lot of dust around it, and below it too.
Yeah. Never seen this dust. We've never been able to image this before, but now we are. Of course, I'm 10 degrees cooler on the sensor, so we have that much less noise. Temperature is minus 20.6. And I wanted minus 20, so it's going even more. That's good. Let's see if we can... Look at that. Wow. Very nice. Very impressed with this. Let's see if we can reduce... Let's zoom in on this now. This is interesting. I've never... I've taken pictures of this, but it's always been just the orange nebula, the reddish-orange hydrogen emission region. I've never seen all the rest of the detail in here. This is cool.
That's nice.
Izabela, you don't recognize this northern Trifid nebula because I don't think we've ever taken it. I've only imaged it, I think, one other time. And now you see it. You see up here, there's reflection nebula up here. Okay, this star's light is being scattered by the high frequency light's being scattered by this nebulous cloud, this dark cloud.
There's quite a bit of dark nebulosity around that.
That's right.
To the upper left where that reflection is, you mentioned, and above, and across the top, and down below, and to the lower left.
Yeah, there's a lot here. Yep. David Schmidt, thank you for stopping by. That was very kind of you. And I will talk to you again. I hope your daughter has a good time at cheerleader tryouts. I hope she kicks butt, man. Not a problem, David. You're more than welcome.
See you, David.
I never thought this had the makings of a very good object, but it does.
Yeah.
This can be a beautiful, subtle thing with nice, beautiful reflection nebula in it. one of these days, guys, I'm gonna just bite the bullet and start taking 1 and 2 minute exposures. I might do it. I'll do it on my own first when I do a private stream, because I don't want to have you hanging waiting for 2 minutes for something to come in. All right. So, but I'll do it on my own. Us astronomers, we are crazy people, let me tell you. Alright, this is the 15th exposure, 15th and final. Okay, and this is the Northern Trifid Nebula, and we will save it. Save exactly as seen. Excellent. All right, very cool.
Thank you for sharing tonight, Mark.
Yeah, no, this was really enjoyable. I'm pretty happy with how it all turned out. So,
I'm going to try to get to bed.
You are?
Yeah.
Oh, well, I guess we have to actually play our music. This is the end.
You're not going to do yet one more?
No, that was the one more. That was the encore.
Okay.
Okay, guys. Once again, you have wasted a wonderful couple of hours with us. Actually, 3.5 of them. And I hope you enjoyed the stream tonight. SkyTour LiveStream is brought to you by all the good people that keep SkyTour LiveStream up and running. So we only run on your generosity too. So, you know, and your attendance. When you attend, it makes all the difference. Thank you, guys. And I will see you again. And well, when you go out, make sure you keep looking up. And if you can't see anything, come here. We'll show you stuff. Good night, everybody.
Good night, everybody.